Hello, and welcome back to Sleepy Science, where we explore the universe's most profound mysteries with a gentle voice and a peaceful heart. Tonight, we're embarking on a journey to the places where stars are born, where darkness becomes light, and where silence holds the power of creation itself. Right now, 7,000 light years away, inside a cloud darker than any night you've ever known, something extraordinary is happening. A region of space 300 times larger than our entire solar system is collapsing in on itself. The temperature is 436 degrees below 0 Fahrenheit. There's no sound, no light visible to human eyes. Yet within this freezing darkness, within this cosmic womb of hydrogen and dust, hundreds of stars are quietly being born. These are the stellar nurseries, the maternity wards of the universe. And tonight, we're going to understand how they work, why they exist, and what they mean for everything we see in the night sky. If you're finding peace in this journey through the cosmos, I'd be grateful if you would take a moment to like this video and subscribe to the channel. It helps us continue creating these gentle explorations of science, and it lets me know you're out there listening under the stars with me. Let's begin our story, where all stars begin in the vast cold darkness between the points of light. When you look up at the night sky, what you're seeing is deceptive. The stars appear as individual points of light scattered across the darkness, like diamonds on black velvet. But this view hides one of the universe's most important truths. Stars are not randomly distributed. They're not cosmic accidents appearing wherever they please. Every single star you see, including our own sun, was born in a stellar nursery, a specific type of cosmic environment that exists in the dark spaces between the lights. The first person to truly document these birthplaces wasn't looking for them at all. In 1774, a French astronomer named Charles Messier was hunting for comets. Comets were his passion, his obsession, and fuzzy patches of light in his telescope were frustrating obstacles. To avoid wasting time on these false comets, he began cataloging them. He didn't realize it at the time, but many of these fuzzy patches were stellar nurseries regions where stars were being born by the thousands. His catalog, meant as a list of things to ignore, became one of astronomy's most important documents. Messier Object 42. The Orion Nebula is the nearest massive stellar nursery to Earth, a cosmic maternity ward just 1,344 light-years away. But it would take another 150 years before we truly understood what these nebulae were. In the 1920s, Edwin Hubble, using the newly constructed 100-inch telescope on Mount Wilson, began resolving individual stars within these clouds. He proved that some nebulae were distant galaxies while others were clouds within our own Milky Way. Among those clouds, some were doing something remarkable. They were glowing not from reflected light, but from the energy of newborn stars hidden within them. These were stellar nurseries in action. So, what exactly is a stellar nursery? The term itself is almost too gentle for what these places really are. Imagine a region of space so massive that it contains enough material to create 10,000 stars like our sun. Now, imagine that entire region is collapsing, fragmenting, heating up, and exploding with stellar winds and radiation, all while appearing perfectly serene to the distant observer. That's the paradox of stellar nurseries. They're simultaneously the quietest and most violent places in the galaxy. At their core, stellar nurseries are molecular clouds, vast accumulations of hydrogen molecules, helium, and cosmic dust. The word cloud is almost misleading. These aren't wispy, ephemeral things like the clouds in Earth's atmosphere. They're structures so massive that they shape the spiral arms of galaxies. A single stellar nursery can stretch across hundreds of light years and contain a mass equivalent to 10 million suns. Yet, despite this incredible mass, they're extraordinarily diffuse. If you were somehow standing inside a stellar nursery, you wouldn't know it. The density is so low that the best vacuum chambers on Earth are far denser. Let me give you a comparison that makes this real. Our entire solar system, from the Sun to the orbit of Neptune, spans about 60 astronomical units, roughly 5.5 billion miles. The Orion Nebula, one of the more compact stellar nurseries, spans 24 light-years. That's approximately 140 trillion miles, or 25,000 times the diameter of our solar system. And Orion is considered small. The Carina Nebula, another famous stellar nursery, stretches across 300 light-years. If you tried to drive across it at highway speed, assuming you could somehow maintain 65 miles per hour through space, the journey would take 3 billion years. The universe itself is only 13.8 billion years old. These vast structures come in different types, each with its own character and role in star formation. Dark nebulae like the Coal Sack or the Horsehead Nebula are molecular clouds so dense with dust that they block all the light from stars behind them. They appear as voids against the starry background, dark patches where no stars shine. But this darkness is deceptive. Inside these clouds, invisible to optical telescopes, stars are forming. The dust that blocks visible light is the very material from which planets will eventually form. Then there are the emission nebulae, like the famous Eagle Nebula or the Lagoon Nebula. These glow with vivid colors, reds and blues and greens, created by the intense ultraviolet light from young massive stars energizing the surrounding gas. The gas absorbs this high-energy light and re-emits it at specific wavelengths, creating the spectacular colors we see in photographs. These are stellar nurseries caught in the act, where star formation is so vigorous that the newborn stars are already beginning to destroy the very clouds that created them. Here's something that surprises most people when they first learn it. When we see these beautiful images of nebulae, the pillars of creation in the Eagle Nebula, the delicate structures of the Carina Nebula, we're looking at things that probably don't exist anymore, at least not in the form we see. Light takes time to travel, and these nurseries are thousands of light years away. The pillars of creation are 7,000 light years distant. The light we see from them today left those structures 7,000 years ago, around the time humans were just beginning to develop agriculture. In the actual present moment, those pillars might have been destroyed by a supernova shockwave or eroded away by stellar winds. We won't know for another 7,000 years. This time delay gives stellar nurseries an almost dreamlike quality. They exist in our past and our present simultaneously. We see them as they were not, as they are, ghosts of creation haunting the night sky. The closest stellar nursery to Earth is the Taurus molecular cloud, just 430 light-years away in the constellation Taurus. It's not as spectacular as Orion or Carina. It doesn't glow with vibrant colors or tower in vast pillars, but it's forming stars right now, low-mass stars similar to our sun. If you were to observe it with an infrared telescope, you'd see dozens of protostars, stellar embryos wrapped in cocoons of gas and dust, slowly accumulating mass and warming up. In a few million years, many of these will become stable stars, possibly with their own planetary systems, possibly with worlds that could harbor life. Think about that for a moment. 430 light-years away, the universe is creating new solar systems. New Earths might be forming. The atoms that will one day comprise alien oceans or alien atmospheres are currently swirling in disks around infant stars. And this isn't happening in some distant, unreachable part of the universe. In cosmic terms, the Taurus molecular cloud is right next door. But here's where the story becomes even more personal. Our own sun, the star that makes life on Earth possible, was born in a stellar nursery approximately 4.6 billion years ago. We know this from analyzing meteorites, the leftover debris from the solar system's formation. These ancient rocks contain isotopes of elements that could only have been created in a supernova explosion, and the isotopes hadn't had time to decay very much before they were incorporated into solid matter. This tells us something profound. Our sun was born in a stellar nursery that had recently been enriched by a supernova. Somewhere in our cosmic neighborhood, a massive star exploded. Its shockwave triggered the collapse of a nearby molecular cloud. And within that cloud, our solar system began to form. That stellar nursery is long gone now. The stars born within it, including our sun, have drifted apart over billions of years, scattered across the galaxy by gravitational interactions. Our sun's siblings, the thousands of other stars that formed in the same cloud at the same time, are now spread across hundreds of light years. Some of them might still exist. Some have already ended their lives in spectacular deaths. We're searching for them, looking for stars with the same chemical composition and the same age as the sun, trying to reconstruct our family tree. A few candidates have been found, but the search continues. There's something deeply moving about this. We're not just residents of a solar system orbiting a star. We're part of a scattered family, orphans of a nursery that dissolved billions of years ago, each carrying within us, within the atoms of our bodies, the memory of that common origin. When we study stellar nurseries, we're not just learning about distant cosmic phenomena. We're investigating our own history, trying to understand the conditions that led to our existence. Every stellar nursery is in some sense a mirror of our past. As we close this first part of our journey, I want you to hold this image in your mind. Across the galaxy in hundreds of vast molecular clouds, the universe is creating stars. In regions of space so cold that all motion nearly ceases, gravity is patiently gathering matter, compressing it, warming it, preparing it for ignition. In darkness, light is being born. In silence, the future is taking shape. And somewhere among those countless forming stars, there might be another solar system beginning its story. Another world preparing to host life. Another consciousness that will one day look up at its own night sky and wonder about its origins. The stellar nurseries are working right now, continuing the process that created our sun, our earth, and us. And in the next part of our journey, we'll look deeper into these cosmic wombs and understand exactly what they're made of, the precise recipe the universe uses to create stars. The ingredients might surprise you because hidden within the cold hydrogen and dust are the building blocks of life itself. If you could gather a teaspoon of material from the heart of a stellar nursery and somehow bring it back to Earth, do you know what you'd have? Almost nothing. The vacuum would be so complete that the best laboratories on our planet couldn't replicate it. Yet that near nothingness spread across light years contains everything needed to build stars, planets, and eventually life itself. The recipe for creation isn't written in exotic matter or mysterious dark energy. It's written in the simplest elements in the universe, hydrogen and helium mixed with a tiny fraction of cosmic dust. But the proportions matter. The temperature matters, and the presence of that dust, that seemingly insignificant 2%, makes all the difference between a cloud that drifts forever and a cloud that collapses into stars. Tonight we're going to examine the exact ingredients the universe uses to create stars. We'll understand why molecular clouds are simultaneously empty and massive, why they're colder than the darkest reaches of the outer solar system, and why that microscopic dust plays a role far more important than its tiny fraction would suggest. This is the chemistry of creation, and it's more precise than you might imagine. If this exploration into the cosmic recipe resonates with you, if you're finding wonder in these details, please consider liking this video and subscribing. Your support allows us to keep diving deep into these beautiful mysteries together. Let's start with the dominant ingredient, the one that makes up 70% of every stellar nursery in the universe: molecular hydrogen. H2 hydrogen atoms bonded together. This might sound straightforward, but here's something remarkable. For most of cosmic history, molecular hydrogen didn't exist. In the immediate aftermath of the Big Bang, the universe was too hot for atoms to form at all. It took 380,000 years for the universe to cool enough for electrons to settle into orbit around protons, creating the first hydrogen atoms. But molecular hydrogen, two atoms bonded together, requires even more specific conditions. It needs cold temperatures, it needs time, and crucially, it needs dust. This is one of those beautiful cosmic ironies. Hydrogen is the first and simplest element created in the Big Bang itself. But molecular hydrogen, the form that dominates stellar nurseries, can't form efficiently without heavier elements. Elements that didn't exist in the early universe and had to be created inside stars and scattered by supernovae. The universe needed its first generation of stars to live and die before efficient star formation could begin. The cosmos had to learn how to make stars by making them imperfectly first. In a molecular cloud, today hydrogen molecules outnumber everything else by an enormous margin. If you could count every particle in a cubic meter of a stellar nursery, you'd find about 300 million hydrogen molecules. That might sound like a lot, until you realize that a cubic meter of air at sea level on Earth contains about 25 quintillion molecules. That's 25 with 18 zeros after it. The stellar nursery is 8 trillion times less dense than the air you're breathing right now. It's essentially a perfect vacuum by any terrestrial standard. Yet, because these clouds are so vast, that tiny density adds up to staggering mass. The Orion Molecular Cloud Complex, the large structure containing the famous Orion Nebula, has a total mass of about 100,000 times the mass of our Sun. The Carina Nebula contains enough material to create several 100,000 stars. The universe is working with incredibly diffuse raw materials, but it's working at scales that dwarf human comprehension. The second ingredient is helium, making up about 28% of the molecular cloud's mass. Helium is cosmically abundant because it was created in the Big Bang alongside hydrogen. In the first 3 minutes after the universe began, when temperatures were still in the billions of degrees, protons and neutrons were fusing together to form helium nuclei. By the time the universe was 20 minutes old, about 25% of all matter by mass had been converted to helium. That primordial helium is still with us, mixed into every molecular cloud, every star, every planet. Helium plays a quieter role than hydrogen in star formation. It doesn't form molecules easily, it doesn't radiate energy efficiently, and it doesn't contribute much to the cloud's ability to cool and collapse. But it's always there, a silent partner, adding mass and contributing to the eventual composition of whatever stars emerge. When our Sun formed 4.6 billion years ago, about 28% of its mass was helium inherited directly from the Big Bang, unchanged and unprocessed for 9 billion years. Now, we come to the most fascinating ingredient, the one that makes up only 2% of the cloud's mass, but plays an outsized role in star formation: cosmic dust. When astronomers first started talking about cosmic dust, the term sounded almost poetic, but vague. What exactly is cosmic dust? Where does it come from? Why does it matter? Cosmic dust is not a single substance. It's a mixture of tiny solid particles, typically about 1 micrometer, across about 1/100th the width of a human hair. These grains are composed of silicates similar to sand on Earth, carbon in the form of graphite, or even tiny diamonds and ices, frozen water, ammonia, methane, and carbon dioxide coating the grain surfaces. Every speck of cosmic dust has a history. The silicate grains were forged in the atmospheres of dying red giant stars, puffed off into space as these stars shed their outer layers. The carbon grains came from stars even more exotic, carbon-rich giants, where carbon became more abundant than oxygen, allowing soot-like particles to form. The ices accumulated later as these grains drifted through the cold molecular clouds, and simple molecules froze onto their surfaces. If you could examine a single grain of cosmic dust under a microscope, you'd see layers of material, each layer telling a story of a different cosmic environment. The core might be a silicate crystal formed in a red giant 5 billion years ago. Around that might be a layer of carbon from a different star, and coating everything a thin layer of ice accumulated over millions of years, drifting through interstellar space. Each grain is a tiny cosmic artifact, carrying the chemical history of the galaxy. These dust grains do something crucial for star formation. They allow molecular clouds to cool down. Here's why that matters. For a cloud to collapse under its own gravity, it needs to lose energy. If the cloud is too hot, The random motion of particles creates pressure that counteracts gravity. The cloud needs to radiate away its thermal energy, cooling down until gravity can win. Hydrogen molecules can do this, but only slowly and under specific conditions. Dust grains are far more efficient. They absorb energy from collisions with gas molecules, then radiate that energy away as infrared light. Dust turns molecular clouds into enormous slow-motion refrigerators, cooling them from 50 degrees Kelvin down to 10 degrees Kelvin, from negative 370 degrees Fahrenheit down to negative 441 degrees Fahrenheit. Let me give you a comparison that makes this temperature real. The average surface temperature on Pluto, the cold distant dwarf planet at the edge of our solar system, is about 44 Kelvin, negative 380 degrees Fahrenheit. The coldest temperature ever recorded on Earth at a Soviet research station in Antarctica in 1983 was negative 128.6 degrees Fahrenheit. The molecular clouds where stars are born are more than 300 degrees colder than that Antarctic record, colder than any natural environment in our solar system, except for the surfaces of distant moons in the outer reaches. At these temperatures, almost all motion stops. Atoms and molecules move in slow, lazy drifts. Chemical reactions that would happen instantly at room temperature take thousands of years. Time itself seems to slow down. And yet, in this frozen stillness, creation is possible. The cold allows gravity to gather material without being fought by thermal pressure. Stellar nurseries are cold because they need to be. Warmth is the enemy of star formation until the very end, when compression finally ignites fusion. But here's something that surprised astronomers when they first discovered it in the 1960s and 70s. Those dust grains with their icy coatings are doing chemistry. Despite the incredible cold, despite the incredibly low density complex, molecules are forming on the surfaces of dust grains. Radio telescopes tuned to specific frequencies began detecting emission lines from molecules that shouldn't exist in interstellar space. Formaldehyde, methanol, ethanol, formic acid, and eventually amino acids, the building blocks of proteins. In 1994, scientists analyzed samples from the Murchison meteorite, a rock that fell in Australia in 1969, and contain pristine material from the early solar system. They found more than 90 different amino acids, including some that are essential for life on Earth. These amino acids weren't created on Earth. They were created in the molecular cloud where our solar system formed, assembled on the surfaces of dust grains in the freezing darkness of space. Think about what this means. The chemistry of life began before Earth existed. The molecules that would eventually be assembled into proteins, DNA, and living cells were floating in the stellar nursery where our sun was born. When the Earth formed and was bombarded by asteroids and comets in its early history, some of those impacts delivered organic molecules created in space. The boundary between stellar nursery chemistry and the chemistry of life is not as clear as we once thought. In 2008, the Spitzer Space Telescope discovered large organic molecules in stellar nurseries, complex carbon structures similar to the ones found in living organisms. In 2012, scientists announced the detection of glycolaldehyde, a simple sugar molecule in a stellar nursery 12,000 light-years away. The universe is doing organic chemistry on vast scales, seeding molecular clouds with the precursors to life. This discovery changes how we think about life's origins. We used to imagine that life began on Earth through fortunate chemistry in warm ponds or deep-sea vents. But increasingly, it looks like the chemistry of life began in space in the coldest, emptiest environments imaginable billions of years before Earth existed. Life didn't emerge despite the hostile conditions of space. It emerged because of the unique conditions in molecular clouds where dust grains provided surfaces for chemical reactions, where ice mantles protected molecules from destructive radiation, and where vast timescales allowed even incredibly slow reactions to proceed. There's a common misconception about stellar nurseries that I want to address directly. Many people, when they first hear about molecular clouds, imagine them as dense, almost solid structures like storm clouds, but in space. The reality is the opposite. If you were somehow floating inside a molecular cloud, you wouldn't see clouds of gas swirling around you. You wouldn't feel pressure or resistance. You'd see absolute blackness in every direction because the dust blocks all external light, but the cloud itself would be completely invisible. You could wave your hand through the space around you and encounter on average one dust grain every few meters. The cloud is so diffuse that it's barely there at all. Yet, this near nothingness is gravitationally bound. The entire structure, hundreds or thousands of solar masses of material, spread across light years, is slowly pulling itself together. Gravity operates patiently. It doesn't need density. It only needs mass and time. Given enough of both, it can transform the emptiest regions of space into stellar nurseries. The Taurus molecular cloud, which we mentioned earlier, as the nearest stellar nursery, has been studied in extraordinary detail. Astronomers have mapped its density structure, its temperature variations, its chemical composition. They've found that it's not uniform. There are denser clumps embedded in more diffuse material, and within those clumps, even denser cores, where individual stars are beginning to form. The cloud looks less like a single object and more like a hierarchy of structures, clouds, within clouds, each level slightly denser and more organized than the last. This hierarchical structure is key to understanding how molecular clouds create so many stars at once. The cloud doesn't collapse as a whole. Instead, it fragments. Denser regions collapse faster, pulling in material from their surroundings, growing into stellar cores, while the rest of the cloud continues its slower collapse. This is why stellar nurseries produce clusters of stars rather than single stars. The fragmentation is built into the process. As we reach the end of this exploration of cosmic ingredients, I want you to appreciate the precision involved. The universe isn't haphazardly throwing matter together and hoping for stars. The proportions matter. 70% hydrogen, 28% helium, 2% dust, and heavy elements. This isn't random. This ratio comes from the Big Bang, from generations of stellar evolution, from billions of years of cosmic chemical enrichment. If the proportions were significantly different, stellar nurseries wouldn't work the way they do. Too little dust and clouds couldn't cool efficiently. Too much, and forming stars would be shrouded so completely that their radiation couldn't clear the surrounding material. The recipe is precise because it's been refined over cosmic history. The universe has been making stars for more than 13 billion years, and the process has optimized itself through countless cycles of birth and death, creation and destruction. Now that we understand what stellar nurseries are made of, the next question becomes even more compelling. These clouds, these vast accumulations of cold hydrogen and dust, can drift through space for millions of years without changing, stable and serene. So, what breaks the equilibrium? What triggers the collapse? In the next part of our journey, we'll discover that sometimes the death of one star becomes the spark that ignites the birth of thousands more. And we'll trace the invisible hand of gravity as it begins its patient work of gathering matter and compressing it toward the moment of creation. 3,000 years ago, a star 20 times the mass of our sun reached the end of its life in a distant spiral arm of the Milky Way. Its core collapsed in a fraction of a second, and the star exploded, releasing more energy in a few minutes than our sun will emit in its entire 10 billion year lifetime. The shock wave from that explosion, moving at thousands of miles per second, expanded outward into space, and 500 years later, that shock wave slammed into a nearby molecular cloud, a cloud that had been drifting peacefully for millions of years. The impact compressed the gas, increased its density, and triggered something that couldn't be stopped. The cloud began to collapse. Within that single violent moment, the fates of thousands of future stars were sealed. This is how it begins, not with a whisper, but with a cosmic shockwave, a disturbance so powerful it can reshape entire regions of the galaxy. But supernovae aren't the only triggers. Molecular clouds can be pushed into collapse by collisions with other clouds, by the spiral arms of galaxies compressing them as they pass through, even by the pressure of intense starlight from nearby massive stars. The universe has many ways of breaking the balance, many methods of starting the cascade that leads to star formation. And once it starts, gravity takes over, patient and inexorable, pulling matter together in a process that will last hundreds of thousands of years. If you're captivated by these cosmic triggers, these moments when the universe shifts from stillness to creation, please take a moment to like this video and subscribe to the channel. Your engagement helps this content reach others who, like you, find peace and wonder in understanding how the cosmos works. The story of stellar birth begins with understanding a delicate balance. Every molecular cloud exists in a state of equilibrium between two opposing forces. Gravity is always trying to pull the cloud together, to compress it to make it denser. But thermal pressure, the random motion of gas molecules, pushes outward, resisting compression. As long as these forces are balanced, the cloud remains stable. It can drift through space for tens of millions of years without changing significantly, a frozen tableau matter, suspended between collapse and dispersal. In the 1920s, a British physicist named James Jeans worked out the mathematics of this balance. He calculated the precise conditions under which a cloud would become unstable and begin to collapse. His criterion, now called the Jeans instability, or the Jeans criterion, depends on just a few factors: the cloud's mass, its temperature, its density, and its chemical composition. If a cloud exceeds a certain critical mass for its given temperature and density, gravity wins. The cloud becomes unstable and begins to collapse. If it's below that critical mass, pressure wins, and the cloud either remains stable or disperses. The Jeans mass, as this critical threshold, is called changes depending on conditions. For a typical molecular cloud with a temperature of 10 Kelvin and a density of a few hundred molecules per cubic centimeter, the Jeans mass is about 1 solar mass. This means that regions of the cloud containing at least one sun's worth of material can potentially collapse to form a star. Regions with less mass will remain stable unless something changes the conditions. Here's what makes this fascinating. A molecular cloud left entirely to itself might never collapse. It might drift through space forever stable and unchanging, its internal pressure perfectly balanced against gravity. Star formation requires a trigger, an external disturbance that tips the balance. The universe needs an initial push, and it has several ways of providing that push. The most dramatic trigger is a supernova explosion. When a massive star explodes, it doesn't just brighten the sky for a few weeks. It sends a shockwave expanding outward at speeds up to 10,000 miles per second, about 5% the speed of light. This shockwave carries enormous momentum and energy. When it encounters a molecular cloud, it compresses the gas at the cloud's edge, suddenly increasing the density. Remember the Jeans criterion: if you increase density while keeping temperature relatively constant, the critical mass for collapse decreases. Regions that were previously stable suddenly become unstable. They begin to collapse and star formation begins. We can see this process happening in real time, or at least in astronomical real time, in a region called IC443. This is a supernova remnant about 5,000 light-years away in the constellation Gemini. The supernova that created it exploded somewhere between 3,000 and 30,000 years ago. The exact timing is still debated, and its shockwave is still expanding outward, now spanning about 50 light-years. At the edges of this expanding remnant, astronomers have detected dense molecular clouds. And within those clouds, they've found infrared signatures of protostars, young stellar objects in the earliest stages of formation. The supernova triggered star formation, and we're watching it unfold. But here's something even more remarkable. The supernova didn't just trigger star formation randomly. It enriched the molecular cloud with heavy elements, the products of nuclear fusion that occurred inside the massive star during its lifetime and in the explosion itself. These heavy elements, carbon, oxygen, silicon, iron, and dozens of others, were blasted into the surrounding space. When new stars form in that enriched material, they inherit a higher metallicity, a greater abundance of elements heavier than helium. And higher metallicity affects everything: how efficiently the gas cools, how planets form, even the possibility of life. Our own solar system formed in material enriched by at least one nearby supernova, possibly several. We know this because meteorites contain short-lived radioactive isotopes atoms that decay quickly on cosmic timescales. Aluminum-26, for example, has a half-life of only 717,000 years. The presence of aluminum-26 in the oldest meteorites tells us that a supernova must have exploded within a few million years, possibly less, before our solar system began to form. That supernova may have done more than just trigger the collapse. It may have enriched the cloud with the heavy elements that eventually formed Earth's iron core, the silicon and oxygen in its rocky mantle, and the trace elements essential for life. Supernovae are the most violent triggers, but they're not the only ones. Stellar winds from massive young stars can also compress nearby molecular clouds. When a very massive star forms, it begins emitting intense ultraviolet radiation, and powerful stellar winds, streams of charged particles flowing outward at hundreds of miles per second. These winds push against the surrounding gas, creating expanding bubbles of hot ionized material. At the edges of these bubbles, the gas piles up, becomes compressed, and can trigger new star formation. The massive star, in a sense, propagates its own kind, creating conditions for more stars to form in a ripple effect, spreading outward. We see this happening in the Carina Nebula, that vast stellar nursery we mentioned earlier. At the heart of Carina is a cluster of extremely massive stars, including Eta Carinae, one of the most massive and luminous stars in our galaxy. These stars are blasting the surrounding nebula with radiation and stellar winds, carving out vast cavities and compressing the gas at the cavity edges. All around the periphery of these cavities, new stars are forming, triggered by the pressure from their massive neighbors. It's a self-perpetuating process. The first generation of stars creates the conditions for the second generation, which in turn may trigger a third. This brings us to one of the most elegant concepts in astrophysics, the idea of triggered star formation, or sequential star formation. Imagine a molecular cloud that's initially stable just below the threshold for collapse. A nearby supernova or a passing spiral arm compresses part of the cloud, triggering the formation of the first generation of stars. Some of those stars are massive, and they quickly, in just a few million years, begin emitting intense radiation and winds. This radiation and wind compress adjacent regions of the still intact molecular cloud, triggering a second generation of star formation. That second generation in turn may trigger a third generation, and so on. Star formation becomes a propagating wave spreading through the molecular cloud over tens of millions of years. We've observed this sequential pattern in several stellar nurseries. The ages of stars within a single nebula aren't uniform. There are older stars in one region and progressively younger stars spreading outward like ripples from a stone thrown into water. The Orion Molecular Cloud Complex shows this pattern beautifully. The oldest stars are about 10 million years old, while the youngest are still forming today. Star formation has been propagating through this region for millions of years, triggered and re-triggered in a cascade of creation. But molecular clouds don't need external triggers to collapse. Sometimes they trigger themselves. As a cloud drifts through the galaxy, it encounters regions of varying density in the interstellar medium. When a cloud enters a denser region or collides with another cloud, the collision can provide the compression needed to exceed the gene's mass. Two clouds, each stable on its own, can merge and become unstable together. Their combined mass and increased density tip the balance, and gravitational collapse begins. Galactic spiral arms play a crucial role in this process. The spiral arms of galaxies like the Milky Way aren't permanent structures. They're density waves regions where stars' gas and dust pile up temporarily as they orbit the galactic center at different speeds. When a molecular cloud enters a spiral arm, it encounters higher ambient pressure. The cloud gets compressed, its density increases, and if conditions are right, it begins to collapse. This is why spiral arms are often lined with stellar nurseries, bright nebulae glowing with the light of young stars. The spiral arms are cosmic assembly lines for star formation. Now, here's where the process becomes even more intricate. Once a molecular cloud begins to collapse, it doesn't collapse uniformly. Remember, these clouds aren't smooth and homogeneous. They have density variations, clumps, and filaments of slightly denser material embedded in more diffuse gas. When the cloud as a whole begins to collapse, these denser regions collapse faster. They have higher gravity relative to their pressure support, so they pull in material more quickly. The cloud fragments breaking up into hundreds or thousands of smaller collapsing regions, each one potentially forming a star or a small cluster of stars. This fragmentation process was first understood theoretically in the 1970s, but it wasn't until the 2000s that telescopes became powerful enough to observe it directly. The Herschel Space Telescope, which operated from 2009 to 2013, mapped stellar nurseries in infrared light, seeing through the dust to reveal the internal structure of collapsing clouds. What Herschel found was stunning. Molecular clouds are filled with filamentary structures, long, thin threads of dense gas stretching across light years. Along these filaments at regular intervals are dense knots where the filaments intersect, or where material has accumulated. These knots are the sites of star formation. Each knot is a fragment of the original cloud, now collapsing independently to form one or more stars. The timescale for this initial collapse is surprisingly long. You might think that once gravity takes over, the cloud would collapse quickly. But remember, we're dealing with incredibly diffuse material. Even though gravity is the only significant force, the cloud is so spread out that it takes time for material to fall inward. For a typical stellar nursery, the initial collapse from the moment the trigger occurs until the cloud fragments into individual stellar cores takes about 1 million years. That's fast on cosmic timescales, but glacially slow by human standards. During this million-year collapse, the cloud undergoes profound changes. As material falls inward, gravitational potential energy converts to kinetic energy and then to heat. The cloud begins to warm up. Not dramatically at first, the temperature might rise from 10 Kelvin to 50. Kelvin's still unimaginably cold by human standards, but enough to change the physics. Warmer gas emits more radiation, which carries away energy, allowing further collapse. It's a delicate balance. Too much heating and the collapse stalls. Too much cooling and the collapse accelerates. The dust plays another crucial role here. As the cloud collapses and warms, the dust grains begin to radiate more efficiently in the infrared. This radiation carries energy away from the collapsing core, preventing it from heating up too quickly. The dust acts as a thermostat, regulating the temperature and allowing the collapse to continue smoothly. Without dust, stellar nurseries wouldn't work nearly as well. The gas would heat up too quickly, pressure would build, and the collapse might stall before stars could form. There's a beautiful domino effect in star formation that I want you to appreciate. A massive star dies in a supernova. Its shockwave triggers star formation in a nearby cloud. Among the newly formed stars are more massive stars. These massive stars live fast and die young, exploding as supernovae themselves within just a few million years. Their explosions trigger more star formation in adjacent clouds. The process repeats, spreading through entire regions of the galaxy. Star formation becomes self-sustaining, a chain reaction of creation fueled by destruction. We see evidence of this in regions called OB associations, loose groupings of hot, massive O-type and B-type stars scattered across hundreds of light years. These stars weren't born in a single stellar nursery. They were born in multiple nurseries, each triggered by the previous generation. The entire region shows a pattern of sequential star formation, with older stars in one area and younger stars spreading outward. The Scorpius-Centaurus OB association, the nearest such region to Earth at about 400 light-years away, shows this pattern clearly. Star formation has been sweeping through this region for the past 15 million years, and it's still ongoing. Let me address a common misconception. Many people think that once a molecular cloud starts to collapse, it inevitably forms stars. But that's not quite true. Collapse can be halted or even reversed if conditions change. If a nearby massive star suddenly begins emitting intense radiation, it can heat the collapsing cloud, increasing thermal pressure and potentially stopping the collapse. If the cloud collides with a high-velocity stream of gas from a galactic wind, the collision can disrupt the collapsing structure. Star formation is not inevitable even after collapse begins. The universe is full of failed stellar nurseries clouds that began to collapse but were disrupted before stars could form. As this part of our journey comes to a close, consider the intricate choreography required for star formation. The universe needs clouds of the right mass, temperature, and composition. It needs triggers to initiate collapse, whether from supernovas, stellar winds, or galactic dynamics. It needs time, typically 1 million years or more, for the collapse to proceed. And it needs the collapse to be regulated, carefully cooling, but not too quickly, fragmenting, but not too much, until finally individual cores become dense and hot enough for the next phase to begin. What happens in those cores, how they evolve from cold, dark fragments into glowing protostars, is a transformation as profound as any in the cosmos. And it's the stage we'll explore next as we watch the embryonic stars take their first tentative steps toward ignition. Deep within, a collapsing fragment of a molecular cloud, hidden behind layers of dust, so thick that no optical telescope could ever see it, something remarkable is taking shape. It doesn't look like a star yet. It has no surface, no defined boundary, just a dense core of gas slowly accumulating mass from the surrounding material. Its temperature at the center has climbed to a few thousand degrees, hot enough to glow a dull red if you could somehow see it, but still millions of degrees away from igniting fusion. This object exists in a twilight state between cloud and star, neither fully one nor the other. Astronomers call it a protostar, and it will remain in this embryonic stage for hundreds of thousands of years, perhaps millions, slowly growing, slowly warming, slowly preparing for the moment when it will finally awaken and become a true star. But the journey from cloud fragment to protostar is not simple, and the protostar's evolution follows a path as intricate and carefully orchestrated as the development of any living embryo. If the hidden drama of stellar embryology fascinates you, if you find yourself drawn to these long, patient transformations happening in the cosmic dark, please consider liking this video and subscribing to Sleepy Science. Your support means we can continue exploring these beautiful processes together. Let's begin by understanding exactly what a protostar is and why astronomers needed to create this category in the first place. For most of human history, we thought stars simply existed. They were eternal, unchanging points of light in the sky. The idea that stars had life cycles, that they were born, evolved, and died, only became accepted in the 20th century. And the concept of the protostar, the intermediate stage between cloud and star, came even later in the 1950s and 60s, as astronomers began to understand the details of star formation. A protostar is defined by what it's doing and what it isn't doing. It's accumulating mass from its surroundings, pulling in gas and dust from the collapsing cloud fragment that surrounds it. It's heating up due to gravitational compression. The energy from infalling material is converting to heat. But crucially, it is not yet fusing hydrogen in its core. That's the key distinction. A protostar is powered by gravity, not by fusion. It glows because it's compressing, not because it's burning nuclear fuel. Once fusion begins, the object transitions from protostar to main sequence star, and its character changes fundamentally. The protostar phase is surprisingly long, and its duration depends entirely on the mass of the forming star. For a star like our Sun, with about 1 solar mass, the protostar phase lasts approximately 10 million years. That sounds like an eternity, but it's actually quite brief on cosmic timescales. For comparison, our Sun will spend 10 billion years as a stable main sequence star, 1,000 times longer than its protostar phase. For more massive stars, the protostar phase is even shorter. A star with 10 solar masses might spend only 100,000 years as a protostar before igniting fusion. For low-mass stars, stars with only 1/10 the mass of the Sun, the protostar phase can last 100 million years or more. Astronomers classify protostars into 4 distinct classes based on their observable properties, particularly how they appear in infrared light. These classes, labeled Class 0, Class 1, Class 2, and Class 3, represent an evolutionary sequence stages that every protostar passes through on its way to becoming a star. Let me walk you through each stage, and you'll see how radically the protostar transforms over time. Class 0 protostars are the youngest, the most deeply embedded in their natal clouds. At this stage, more than half of the system's total mass is still in the surrounding envelope of infalling gas and dust, not yet accreted onto the central protostar. The protostar itself is tiny, perhaps only a few times the size of Jupiter, but it's already remarkably dense. Class 0 protostars are completely invisible at optical and near-infrared wavelengths. The dust surrounding them is so thick that it absorbs all visible light. They can only be detected at far infrared and submillimeter wavelengths, where the thermal emission from the coal dust becomes visible. The Class 0 phase lasts only about 10,000 to 50,000 years, a brief moment in the protostar's evolution, but a crucial one. This is when the protostar is growing most rapidly, doubling or tripling its mass in just a few tens of thousands of years. As the protostar continues to accrete material, it transitions into Class 1. Now, more than half of the system's mass is in the central protostar rather than the envelope. The envelope is thinning, becoming more transparent, and the protostar begins to reveal itself at shorter wavelengths. Class 1 protostars are still heavily obscured, but they can be detected in near-infrared light. They're also developing something new and critically important, an accretion disk. As material falls toward the protostar, it doesn't fall directly inward. It has angular momentum residual rotation from the original cloud's slow spin. This angular momentum prevents the material from falling straight down. Instead, it spirals inward, forming a flattened rotating disk around the protostar. This disk, typically a few hundred astronomical units across, is where planets will eventually form. Every planetary system, including our own solar system, began as an accretion disk around a Class 1 protostar. The accretion disk is not just a passive structure. It's dynamically active, turbulent, and extremely important for the protostar's growth. Material in the disk gradually spirals inward, transported by a process called viscous dissipation. Friction within the disk converts orbital energy into heat, and that heat radiates away, allowing the material to lose energy and spiral closer to the protostar. Eventually, the material reaches the inner edge of the disk and falls onto the protostar's surface in a process called accretion. This accretion releases enormous amounts of energy. When a blob of gas falls from the disk onto the protostar, it can be moving at hundreds of miles per second by the time it hits. The kinetic energy of that impact converts to heat, and the impact site glows intensely in ultraviolet and X-ray light. But something else is happening during the Class 1 phase, something that seems almost contradictory. Even as the protostar is pulling material inward through its accretion disk, it's simultaneously ejecting material outward in powerful bipolar jets. These jet streams of gas moving at tens or even hundreds of miles per second shoot out perpendicular to the accretion disk, creating a stunning cosmic fountain. The jets can extend for light years, carving through the surrounding molecular cloud and creating glowing structures called Herbig-Haro objects, where the jet material slams into the ambient gas. Why does this happen? Why would a protostar that's trying to grow by accreting material simultaneously eject material? The answer lies in magnetic fields. As the protostar rotates and the disk swirls around it, magnetic field lines get twisted and amplified. These magnetic fields channel some of the infalling material, redirecting it away from the protostar and launching it outward along the magnetic poles. The jets serve a crucial function. They carry away angular momentum. Without the jets, the accreting material would spin up the protostar faster and faster, eventually spinning so fast that centrifugal force would prevent further accretion. The jets act as a release valve, allowing the protostar to continue growing without spinning itself apart. One of the most spectacular examples of protostellar jets was discovered in the 1980s in the constellation Orion, an object called HH-34. A Herbig-Haro object showed a clear bipolar jet structure extending nearly half a light year from a central Class 1 protostar. Subsequent observations with the Hubble Space Telescope revealed extraordinary detail. Knots and filaments in the jet, moving at different velocities, shock waves, where faster material overtakes slower material, and bow shocks, where the jet plows into the surrounding gas. The jets from this single protostar have pumped enough energy into the surrounding cloud to heat and ionize gas across a volume hundreds of times larger than our solar system. As the protostar continues to evolve, accreting more mass and slowly clearing its surroundings, it enters the Class 2 phase. This is often called the T Tauri phase, named after T Tauri, the first star of this type to be studied in detail. T Tauri was discovered in 1852 by John Russell Hind, who noticed a new star that hadn't been visible before. What Hind didn't realize was that T Tauri hadn't suddenly appeared. It had always been there, but it had brightened dramatically due to changes in its accretion rate. T Tauri became the prototype for an entire class of young stellar objects. Class 2 protostars have largely dispersed their surrounding envelopes. They're now visible at optical wavelengths, though they're still surrounded by their accretion disks. These disks are now the dominant feature massive structures containing up to 10% of the protostar's mass. The disk is where the real action is happening. Within the disk, dust grains are colliding and sticking together, beginning the slow process of planet formation. Close to the protostar, where temperatures are high, only rocky materials can survive. Farther out beyond the frost line, where temperatures drop below the freezing point of water, ice can condense and giant planet cores can begin to form. The Class 2 phase lasts the longest of any protostellar stage, typically several million years. During this time, the protostar is relatively stable. It's still accreting material from its disk, but at a much slower rate than during the Class 0 and Class 1 phases. The protostar's luminosity comes from a combination of accretion energy and gravitational contraction. As the protostar slowly contracts under its own weight, gravitational potential energy converts to heat, and the core temperature gradually rises. At the beginning of the Class 2 phase, the core temperature might be around 1 million Kelvin. By the end, it's approaching 10 million Kelvin, getting very close to the threshold for hydrogen fusion. In 2014, the Atacama Large Millimeter Array ALMA captured an image that revolutionized our understanding of protoplanetary disks. The target was HL Tauri, a young Class 2 protostar about 450 light-years away. Previous observations had shown that HL Tauri had a disk, but ALMA's unprecedented resolution revealed something stunning. The disk wasn't smooth. It had multiple concentric gaps and rings, dark bands, and bright bands alternating in a pattern that looked almost artificial in its regularity. These gaps are almost certainly being carved by forming planets. As a planet grows within the disk, its gravity clears out a gap, sweeping up material in its orbital path. The H.L. Tari image showed at least 7 distinct gaps, suggesting 7 forming planets, possibly more. And H.L. Tari is less than 1 million years old. Planet formation doesn't wait until star formation is complete. It begins immediately as soon as the disk is stable enough to allow dust grains to accumulate. Finally, we reach Class 3, the last protostellar stage, before the star settles onto the main sequence. Class 3 objects have largely dispersed their accretion disks, or at least thinned them dramatically. Accretion has essentially stopped. The protostar is now fusing deuterium, a heavy isotope of hydrogen in its core. Deuterium fusion doesn't produce much energy. Deuterium is far less abundant than normal hydrogen, but it's a crucial intermediate step. It provides just enough energy to slow the protostar's gravitational contraction, giving it time to complete its pre-main sequence evolution. The star is now visible at all wavelengths, no longer hidden by dust. It appears as a bright variable star, often surrounded by a faint remnant disk of dust and gas, the leftover material from which planets may still be forming. There's a common misconception I should address here. Many people assume that protostars are small, perhaps Earth-sized or Jupiter-sized, and that they grow to sun size only when fusion begins. But that's backwards. Protostars are actually much larger than they will be as main sequence stars. A Class 1 protostar destined to become a sun-like star might have a radius 5 to 10 times larger than the Sun. It's puffy diffuse, not yet fully contracted. As it evolves, it shrinks. By the time it reaches the main sequence and begins steady hydrogen fusion, it will have contracted to approximately its final size. The Sun, as a protostar, was probably larger than Mercury's orbit. As it contracted and heated up, it shrank down to the size we see today. The temperature evolution of a protostar's core is one of the most critical aspects of its development. At the Class 0 stage, the core temperature might be only a few hundred Kelvin, barely warmer than the surrounding cloud. As the protostar accretes mass and contracts, the core temperature rises steadily. By Class 1, it's reached several thousand Kelvin. By Class 2, it's in the hundreds of thousands or even millions of Kelvin. And by late Class 3, it's approaching 10 million Kelvin, the threshold for proton-proton fusion, the reaction that powers stars like our Sun. This gradual heating is essential. If the core heated up too quickly, the protostar would ignite fusion prematurely before it had accreted enough mass to sustain stable fusion. If it heated up too slowly, the protostar might never reach fusion temperatures, and it would become a brown dwarf, a failed star, an object too massive to be a planet, but not massive enough to sustain hydrogen fusion. The timeline has to be just right, and for most protostars, it is. Nature has refined this process over billions of years, and it works remarkably well. Let me give you a comparison that might help you appreciate the timescales involved. Human embryonic development from conception to birth takes about 9 months. If we scale that up proportionally, the protostar phase is equivalent to a pregnancy lasting 10,000 years. Every day of human development corresponds to about 30 years of protostellar evolution. The patience required is beyond human comprehension. We observe protostars at single moments in their million-year development, like seeing a single frame from a movie that lasts 1,000 human lifetimes. Yet we can reconstruct the full story by observing many protostars at different stages. It's like studying human development by looking at many embryos of different ages. We see Class 0 protostars just beginning their journey, Class 1 protostars midway through, and Class 3 protostars nearly ready for birth. By comparing these snapshots, we piece together the full narrative. As we near the end of this exploration into the embryonic life of stars, consider the transformation that's occurred. We started with a cold, dark, collapsing cloud fragment, essentially empty space with a tiny bit of gas. And we've traced its evolution into a glowing, contracting protostar surrounded by a disk, where planets are beginning to form ejecting jets that reshape its environment and steadily heating up toward the moment of nuclear ignition. The protostar is almost ready, its core temperature climbing toward 10 million Kelvin, its mass nearly complete, its surrounding envelope nearly cleared away. And soon, very soon, in cosmic terms, something will happen that changes everything. In the core, at the center of all that accumulated mass, protons will begin to collide with enough energy to overcome their mutual repulsion and fuse together. Nuclear fire will ignite, and the protostar will be born as a true star, beginning a life that could last billions of years, and will witness that moment of ignition and understand exactly what happens when a star finally awakens. In the core of a contracting protostar, pressure and temperature have been climbing for millions of years. The core is now compressed to densities 150 times greater than water squeezed by the immense weight of all the overlying material. The temperature has reached 9 million Kelvin, then 9.5 million, then 9.9 million. Protons, the nuclei of hydrogen atoms, are colliding billions of times per second, bouncing off each other due to their mutual electromagnetic repulsion. But now, at 10 million Kelvin, something different begins to happen. A tiny fraction of collisions, perhaps 1 in every trillion, occurs with just enough energy to overcome that repulsion. 2 protons touch, and in that instant, quantum mechanics allows them to fuse, transforming into deuterium and releasing a burst of energy. Then another fusion occurs, and another, and within minutes, a chain reaction ignites. The core floods with energy, pressure surges outward, and the long gravitational collapse finally halts. The protostar has become a star. Its birthday has arrived, and it will shine steadily for billions of years to come. This is one of the most profound transitions in the universe, the moment when matter becomes light, when gravity's long, patient work finally creates something self-sustaining. And understanding exactly how this moment unfolds reveals truths about energy, matter, and the nature of stars themselves. If you're moved by these moments of cosmic transformation, these thresholds between one state and another, I invite you to like this video and subscribe. Sharing this journey with you makes the exploration even more meaningful. The ignition of fusion is not a sudden event like striking a match. It's a gradual transition that unfolds over thousands of years, a slow awakening rather than an abrupt switch. But there is a definite threshold, a specific temperature and density, where fusion becomes self-sustaining. And understanding that threshold requires us to look at the quantum mechanics of how protons fuse together. Protons carry positive electric charge, and positive charges repel each other. This electromagnetic repulsion is extraordinarily strong at close range. For 2 protons to fuse, they must get close enough for the strong nuclear force to take over. But the strong force only operates at distances less than a femtometer, 1/quadrillionth of a meter. At larger distances, the electromagnetic repulsion dominates, pushing the protons apart. Classical physics says that at temperatures of 10 million Kelvin, protons simply don't have enough kinetic energy to overcome this repulsion. They should bounce off each other forever, never getting close enough to fuse. By classical calculations, fusion should require temperatures of 100 million Kelvin or more. But the universe doesn't obey classical physics at these scales. It obeys quantum mechanics. And quantum mechanics has a loophole called quantum tunneling. In quantum mechanics, particles don't have definite positions. They exist as probability waves spread out over space. There's always a small probability that a particle can be found somewhere it shouldn't be able to reach according to classical physics. When 2 protons approach each other, there's a tiny but non-zero probability that they will quantum tunnel through the electromagnetic barrier and suddenly find themselves close enough for the strong force to grab them. When that happens, fusion occurs. The probability of quantum tunneling is extremely small, At 10 million Kelvin, only about one collision in every 10 to the 20th power, that's 1 in 100 quintillion, results in fusion. But there are so many protons in a stellar core, and they're colliding so frequently that even this tiny probability is enough. In the sun's core right now, about 600 million tons of hydrogen are being converted to helium every single second through this process. 600 million tons every second, and the sun has been doing this for 4.6 billion years, and it still has enough hydrogen to continue for another 5 billion years. The fusion process that powers stars like our sun is called the proton-proton chain, and it proceeds through several steps. First, two protons fuse to form deuterium, a heavy isotope of hydrogen with one proton and one neutron. This step also produces a positron, the antimatter equivalent of an electron, and a neutrino, a nearly massless particle that interacts so weakly with matter that it escapes the sun, immediately carrying away some energy. The positron quickly encounters an electron and annihilates, converting both particles into pure energy in the form of gamma-ray photons. Next, the deuterium nucleus captures another proton, forming helium-3, an isotope of helium, with two protons and one neutron. This reaction releases another gamma-ray photon. Finally, two helium-3 nuclei collide and fuse, forming helium-4, the common stable isotope of helium, with two protons and two neutrons, and releasing two protons back into the mix. The net result of this entire chain is that 4 protons have been converted into one helium-4 nucleus, 2 positrons, 2 neutrinos, and 6 gamma-ray photons. The helium-4 nucleus has slightly less mass than the 4 original protons, about 0.7% less. That missing mass has been converted to energy. According to Einstein's equation, E equals mc squared. 0.7% might not sound like much, but when you're dealing with stellar masses, it's enormous. Every kilogram of hydrogen that fuses releases about 6.3 times 10 to the 14th joules of energy, roughly the energy released by exploding 15,000 tons of TNT. The sun converts 600 million tons of hydrogen per second, releasing an amount of energy that would power human civilization at current consumption rates for several 100,000 years, every single second. When fusion first ignites in a protostar's core, the effect is dramatic. Suddenly, the core is generating its own energy, no longer relying solely on gravitational contraction. This energy creates pressure, pushing outward against the inward pull of gravity. For the first time in the protostar's life, there's a force strong enough to balance gravity. The collapse stops. The star reaches hydrostatic equilibrium, a perfect balance between the outward pressure from fusion and the inward pull of gravity. This balance is remarkably stable. If the fusion rate increases slightly, the core heats up, expands slightly, and the density and temperature drop, slowing the fusion rate back down. If the fusion rate decreases, the core cools, contracts slightly, and the temperature and density rise, speeding fusion back up. The star naturally stabilizes itself, a thermostat built into the physics of stellar structure. But fusion doesn't ignite uniformly throughout the protostar. It begins in the very center where temperature and density are highest and gradually spreads outward as the core heats up. The region where fusion is occurring, called the nuclear burning core, is surprisingly small. In a star like the sun, fusion only occurs in the innermost 15% of the radius, containing only about 35% of the star's total mass. The rest of the star, the outer 65% of the mass, is just sitting there, held up by pressure from below and compressed by its own weight, not participating in fusion at all. The moment when fusion becomes self-sustaining is the star's true birthday, the moment astronomers define as the beginning of its main sequence lifetime. For a sun-like star, this moment typically occurs about 50 million years after the initial cloud collapse began. 50 million years sounds like an eternity, but it's brief compared to the star's subsequent lifetime. the Sun will spend 10 billion years on the main sequence, 200 times longer than it took to get there. The star's birth is accompanied by a violent clearing of its surroundings. The intense ultraviolet radiation and powerful stellar winds from the newborn star begin to ionize and blow away the remaining gas and dust around it. If the star has siblings forming nearby, their combined radiation creates an even more powerful effect. This clearing process is called photoevaporation, and it's one of the main reasons stellar nurseries are self-limiting. The massive stars that form first begin destroying the very cloud that created them, preventing further star formation and eventually dispersing the nursery entirely. One of the most intensively studied examples of this process is the star Fu Orionis. In 1936, this previously faint star suddenly brightened by a factor of 100 over the course of just a few months. Astronomers were baffled. The star remained bright for decades, slowly fading, but still far more luminous than before the outburst. Eventually, they realized what had happened. Fu Orionis is a young star still in its T-Tauri phase, still accreting material from its surrounding disk. The brightening was caused by a sudden dramatic increase in the accretion rate. Material from the disk suddenly dumped onto the star's surface, releasing enormous amounts of gravitational energy and causing the star to brighten dramatically. Fu Orionis is still experiencing this elevated accretion today, nearly 90 years after the outburst began. It's a reminder that stellar birth is not smooth and gradual. It can be punctuated by sudden violent events. Our own sun went through a similar phase called the T-Tauri phase when it was between 1 and 10 million years old. During this time, the young sun was extremely active, producing powerful stellar winds and frequent flares much more violent than the sun today. These winds swept through the inner solar system, blowing away the atmospheres of any planets that had already formed and clearing out leftover gas and dust. This early violent phase shaped the final architecture of our solar system. It's why the inner planets Mercury, Venus, Earth, and Mars are small and rocky, while the outer planets Jupiter, Saturn, Uranus, and Neptune are large and gas-rich. The inner planets lost their primordial hydrogen and helium atmospheres to the young sun's winds, while the outer planets farther from the sun retain theirs. There's an important lesson here about how the star's mass determines its fate. The temperature required to ignite hydrogen fusion is about 10 million Kelvin, and this temperature is only reached if the protostar has accumulated enough mass. The minimum mass for a star, the threshold below which fusion never ignites, is about 75 times the mass of Jupiter, or about 0.075 solar masses. Objects below this threshold are called brown dwarfs, failed stars that glow dimly from the heat of their gravitational contraction, but never achieve sustained fusion. Brown dwarfs are fascinating objects in their own right. They're more massive than planets, but not massive enough to be stars. They form the same way stars do, from collapsing fragments of molecular clouds, but they simply didn't accumulate enough mass to cross the fusion threshold. Brown dwarfs are surprisingly common. Recent surveys suggest there may be billions of them in our galaxy, drifting silently through space, glowing faintly in infrared light, slowly cooling over billions of years. At the other end of the mass spectrum, there's also an upper limit to stellar mass. Above about 150 solar masses, a star becomes unstable. The radiation pressure from fusion in the core becomes so intense that it begins to blow the star apart. Stars more massive than this threshold can't hold themselves together. They shed mass through intense stellar winds until they drop below the threshold. The most massive stars ever observed, like R136A1 in the Large Magellanic Cloud, have masses around 250 to 300 solar masses, but they're losing mass rapidly and will eventually settle down to more stable values. The vast majority of stars, about 75% of all stars in the galaxy, are low-mass stars, red dwarfs, with masses between 0.075 and 0.5 solar masses. These stars burn their hydrogen so slowly that they can live for trillions of years, far longer than the current age of the universe. Some red dwarfs born in the early universe 13 billion years ago are still on the main sequence today and will continue shining for hundreds of billions of years into the future. In a sense, red dwarfs are the universe's ultimate survivors, the stars that will still be shining long after everything else has gone dark. Stars like our Sun, with about 1 solar mass, are actually somewhat rare, making up only about 7% of all stars. And massive stars, those with 10 solar masses or more, are extremely rare, less than 1% of all stars. Yet, despite their rarity, massive stars play an outsized role in galactic evolution. They live fast, burning through their fuel in just a few million years, and they die spectacularly in supernova explosions, enriching the galaxy with heavy elements and triggering new waves of star formation. The ignition of fusion marks another profound shift in the star's evolution, the transition from an object whose properties are determined by its history to an object whose properties are determined by its mass. Before fusion, the protostar's luminosity, temperature, and size depend on how quickly it's accreting material, how fast it's contracting, and other time-dependent factors. But once fusion ignites, the star settles into a state determined almost entirely by its mass. A 1 solar mass star will have a specific luminosity, temperature, and radius, and every other 1 solar mass star in the universe will have almost exactly the same properties. Mass determines everything, and the main sequence is really just a mass sequence stars, arranged by how massive they are. This is why astronomers can learn so much from studying main sequence stars. If we measure a star's surface temperature and luminosity, we can immediately infer its mass, its age, its internal structure, and its future evolution. The physics is that precise, that predictable. As fusion stabilizes and the star settles onto the main sequence, its appearance finally becomes stable. The violent outbursts of the T-Tauri phase gradually subside. The accretion disk is gone, either incorporated into the star, or dispersed into space or used to build planets. The stellar winds become gentler, more like the sun's current solar wind, rather than the gale force winds of its youth. The star's luminosity and temperature stop fluctuating and settle into steady values that will remain nearly constant for billions of years. If you could watch a sun-like star being born in time-lapse, compressing 50 million years into a few minutes, you'd see the dark cloud fragments slowly brighten as gravitational energy converts to heat, flicker with the chaotic accretion of the T-Tauri phase, then suddenly stabilize as fusion ignites and the star reaches equilibrium. That moment of stabilization is the true birth, the moment when the star stops being a transient phenomenon and becomes a stable, long-lived object. 4.6 billion years ago, somewhere in a stellar nursery that no longer exists, this exact process occurred. A fragment of a molecular cloud enriched by a nearby supernova collapsed over tens of millions of years. A protostar formed accreted mass from its disk, ejected jets that carved through the surrounding gas. Fusion ignited, the young sun blazed to life, and its powerful winds cleared the inner solar system. Around the young sun in the remnant disk, dust grains were colliding and sticking together, building pebbles, then boulders, then planetesimals. Within a few tens of millions of years, Earth had formed a ball of molten rock orbiting a newborn star. And now, 4.6 billion years later, we stand on that cooled and solidified rock, looking up at that now middle-aged star, and trying to understand the process that created it and us. The story of stellar birth is our story. We are the children of a stellar nursery born from the same collapse that created our sun. And across the galaxy, the same process continues, new suns igniting new planetary systems, forming perhaps new worlds where future intelligence will one day look up and wonder about their origins. But stars are not born alone, and in the next part of our journey, we'll discover that most stars, including quite possibly our own sun, are born with siblings, brothers and sisters that share the same birthday, the same birthplace, and eventually drift apart across the galaxy, scattered by time and gravity into the vast stellar diaspora. Somewhere in our galaxy, there are stars that share the sun's birthday. They were born in the same stellar nursery from the same collapsing molecular cloud 4.6 billion years ago. They ignited fusion within a few million years of each other, and for a brief cosmic moment, they were part of the same stellar family, a cluster of thousands of young stars orbiting together in space. But gravity is a patient sculptor, and over hundreds of millions of years, those siblings drifted apart. Some were flung outward by gravitational encounters with other stars. Some were pulled away by the tidal forces of the galaxy itself. Today, they're scattered across thousands of light years, strangers to each other, no longer recognizably related. But they carry within them the same chemical signature, the same isotopic fingerprint from the supernova that enriched their birth cloud. If we could find them, analyze their composition, and trace their orbits backward through time, we could reconstruct our sun's family tree and understand what it was like when our star was young, surrounded by siblings in a crowded stellar nursery. This is one of astronomy's great detective stories, searching for lost siblings, and understanding how stellar families are born, evolve, and ultimately disperse. The journey takes us from the most crowded stellar environments in the galaxy to the loneliest stars drifting through the void. If the idea of stellar families of stars born together and scattered by time resonates with you, please take a moment to like this video and subscribe to the channel. These stories of cosmic connection and separation are what make the universe feel less vast and more intimate. Let's start with a fact that surprises most people when they first hear it. The majority of stars in our galaxy are not alone. More than half of all stars exist in binary or multiple star systems, gravitationally bound to one or more companion stars. Our sun orbiting through space by itself, with only planets for company, is actually somewhat unusual. The typical star has at least one stellar companion, and many have 2, 3, or even more. This tells us something profound about how stars form. Stars aren't born in isolation. They're born in groups, often in large groups within stellar nurseries. The fragmentation process we discussed earlier, where a collapsing molecular cloud breaks into smaller pieces, naturally creates multiple stars in close proximity. Sometimes these fragments remain gravitationally bound to each other, forming binary or multiple star systems. Sometimes they're born close enough together that they form a cluster, a gravitationally bound group of stars that orbit a common center of mass. The closest binary star system to Earth is Alpha Centauri, just 4.37 light-years away. Alpha Centauri consists of 3 stars, Alpha Centauri A and B, which orbit each other every 80 years, at an average distance of about 23 astronomical units, similar to the distance between Uranus and the Sun and Proxima Centauri, a small red dwarf orbiting the AB pair at a distance of about 13,000 astronomical units, or about a fifth of a light year. This 3-star system formed together about 6 billion years ago from the same collapsing cloud fragment. They're true siblings bound together by gravity for their entire lives. Binary stars come in many configurations. Some are so close that their surfaces nearly touch, separated by only a few solar diameters. Others, like Alpha Centauri, have separations measured in astronomical units. And some binaries are so widely separated that the 2 stars orbit each other at distances of thousands of astronomical units, taking hundreds of thousands of years to complete a single orbit. These wide binaries are only barely bound, held together by the slightest gravitational thread, and they can be disrupted by passing stars or encounters with molecular clouds. The formation of binary stars is surprisingly common. When a collapsing cloud fragment reaches the protostellar stage, it often has too much angular momentum to collapse into a single star. The rotating material forms an accretion disk, but sometimes the disk itself becomes gravitationally unstable, and fragments forming two or more protostars within the same disk. These protostars accrete material from the disk and from each other, spiraling inward until they reach a stable configuration. This process can create binaries with very close separations, sometimes just a few million miles apart. There's something beautiful about binary star systems when you think about the experience of any planets orbiting them. Imagine living on a world orbiting a binary star. You'd have two suns in your sky, rising and setting at different times, casting double shadows. Depending on the orbital configuration, you might experience periods when both suns are visible, simultaneously providing intense illumination, and periods when only one sun is visible, giving a more gentle light. The seasons on such a world would be extraordinarily complex, determined not just by the planet's axial tilt, but by the changing distance to each star as they orbit. And here's something remarkable we've discovered: planets orbiting binary stars. The Kepler Space Telescope, which operated from 2009 to 2018, found dozens of such systems. One of the most famous is Kepler 16b, a Saturn-sized planet orbiting a binary star system about 200 light-years away. The two stars orbit each other every 41 days, and the planet orbits both stars every 229 days. If you stood on Kepler 16b, you'd see both stars rise and set together, a double sunrise and double sunset. The planet exists in a region of stability, where the gravitational influences of both stars balance out, creating an orbital path that, while complex, is nonetheless stable over millions or billions of years. But binary and multiple star systems are just the smallest scale of stellar groupings. The next scale up is the stellar cluster, and clusters come in two distinct types: open clusters and globular clusters, each with their own characteristics and formation histories. Open clusters are loose groupings of anywhere from a few dozen to a few thousand stars, all born from the same molecular cloud, typically within a region spanning just a few tens of light years. They are called open because the stars are relatively widely separated, not packed tightly together. Open clusters are young, typically between 10 million and a few billion years old, and they're found primarily in the disk of the galaxy along the spiral arms, where star formation is active. The most famous open cluster visible to the naked eye is the Pleiades, also called the Seven Sisters, located about 440 light-years away in the constellation Taurus. The Pleiades cluster contains over 1,000 stars, but only the brightest 6 or 7 are visible without a telescope. The cluster is remarkably young, only about 100 million years old. These stars were born when dinosaurs roamed the Earth, and they're still surrounded by faint wisps of the molecular cloud that created them visible as a blue reflection nebula in long-exposure photographs. The Pleiades are gravitationally bound, meaning all the stars in the cluster are orbiting their common center of mass. Over time, this cluster will gradually disperse. Gravitational interactions between stars will occasionally give one star enough velocity to escape. Encounters with molecular clouds as the cluster orbits the galaxy will strip away some of the outermost members. In about another 250 million years, the Pleiades will have dispersed completely, and its member stars will be scattered across the galaxy, no longer recognizable as a cluster. Another spectacular open cluster is the Hyades, the nearest open cluster to Earth, at only 153 light-years away. The Hyades forms the V-shaped face of Taurus the Bull in our night sky. This cluster is much older than the Pleiades, about 625 million years old, and it's more dispersed. The Hyades contain several hundred stars spread across a region, about 75 light-years in diameter. Because it's so close and so well studied, the Hyades has been crucial for calibrating the cosmic distance ladder. By measuring the distances to Hyades, stars very precisely using parallax astronomers established a baseline for measuring distances to more distant objects. Inside the Orion Nebula, the stellar nursery we've mentioned several times, there's a young open cluster called the Trapezium Cluster, named for its 4 brightest stars, which form a trapezoid shape. The Trapezium Cluster is extraordinarily young, only about 1 million years old, and it's still partially embedded in the nebula that created it. The 4 bright trapezium stars are massive O and B-type stars, and their intense ultraviolet radiation is ionizing and illuminating the surrounding gas, creating the glowing nebula we see. But surrounding those 4 bright stars are more than 2,000 fainter stars, most of them still in their T-Tauri phase, still accreting from their disks, still variable and active. This cluster is a stellar nursery caught in the act. And studying it gives us a window into what our solar system's birth cluster might have looked like 4.6 billion years ago. The dynamics of star clusters are governed by a process called dynamical evolution, and it's essentially stellar billiards played over millions of years. In a cluster, stars are constantly moving, each following its own orbit around the cluster's center of mass. Occasionally, 2 stars pass close to each other, and their mutual gravity deflects their trajectories. Sometimes these encounters involve multiple stars simultaneously, and the gravitational interactions can become quite complex. In some of these encounters, one star gains velocity while another loses it. If a star gains enough velocity, it can exceed the cluster's escape velocity and fly away, never to return. This process, called evaporation, gradually whittles away at the cluster, removing stars one by one, until eventually nothing remains but a loose stream of stars following similar orbits. Computer simulations of cluster evolution show that about 90% of all open clusters dissolve within their first billion years. Only the most massive, most tightly bound clusters survive longer. This means that most stars, including our Sun, were probably born in open clusters that no longer exist. The cluster dispersed billions of years ago, and its member stars are now spread across the galaxy. This brings us to one of modern astronomy's most ambitious projects, finding the Sun's siblings. We know the Sun was born in a cluster. We can estimate that the cluster probably contained a few thousand stars based on typical stellar nursery properties. And we know that cluster dispersed over the past 4.6 billion years. But those sibling stars still exist somewhere in the galaxy. They're still orbiting the galactic center, following paths determined by the same initial conditions that sent the Sun on its current trajectory. If we can find stars with the same age as the Sun, the same chemical composition and orbits that, when traced backward, intersect with the Sun's orbit 4.6 billion years ago, those stars are likely to be the Sun's siblings. In 2014, a team of astronomers announced a promising candidate, HD 1622826, a star about 110 light-years away in the constellation Hercules. It's a G-type star, slightly more massive than the Sun, with a very similar chemical composition. Its age is consistent with the Sun's age, and when its orbit is traced backward, it passes through the same region of the galaxy where the Sun was likely born. HD 1622826 might be our Sun's sibling, a star born in the same nursery, now separated by 110 light-years, and billions of years of orbital evolution. Finding more solar siblings is an ongoing project. Surveys like Gaia, the European Space Agency's mission to map the positions and motions of over 1 billion stars, provide the precise data needed to trace stellar orbits backward through time. As more candidates are identified and analyzed, we'll gradually reconstruct our Sun's family tree and learn more about the environment in which our solar system formed. Now, let's consider the second type of stellar cluster, globular clusters. These are very different from open clusters. Globular clusters are ancient, typically between 10 and 13 billion years old, almost as old as the universe itself. They contain hundreds of thousands to millions of stars, packed into a roughly spherical volume, just tens of light years across. the stellar density in the core of a globular cluster can be 10,000 times higher than in the solar neighborhood. Stars in globular cluster cores are separated by mere light weeks or light days, close enough that stellar encounters and collisions are relatively common. Globular clusters orbit galaxies in large elliptical orbits that take them far above and below the galactic disk. The Milky Way has about 150 known globular clusters, most of them orbiting in the galactic halo. The nearest globular cluster, NGC 6397, is about 7,800 light-years away, much farther than any open cluster. The most spectacular globular cluster in the northern hemisphere is M13, the Great Globular Cluster in Hercules, about 22,000 light-years away. M13 contains several 100,000 stars packed into a sphere about 145 light-years across. At its core, the stellar density is so high that if Earth orbited a star in M13's core, our night sky would contain hundreds of stars, brighter than Sirius, the brightest star in Earth's actual sky. The night would never be truly dark. There would be enough starlight to read, by enough light to cast shadows. Globular clusters formed very early in the universe's history, during the first few billion years after the Big Bang. They were born in the first major wave of star formation, when the universe was smaller and denser, and the conditions for forming massive clusters were more favorable. The stars in globular clusters are metal poor, meaning they have very low abundances of elements heavier than helium. This is because they formed before many generations of supernovae had enriched the interstellar medium with heavy elements. Studying globular cluster stars gives us a window into the early universe, showing us what stars were like when the cosmos was young. Globular clusters are so tightly bound by gravity that they have survived for 10 billion years or more, essentially unchanged. While open clusters disperse over a few 100 million years, globular clusters endure. They are the oldest objects we can see in the night sky, time capsules from the dawn of cosmic history. The contrast between open and globular clusters illustrates two different modes of star formation. Open clusters form in the active spiral arms of galaxies where gas and dust are abundant and star formation is ongoing. They are the product of the galaxy's current activity stars being born right now or in the recent past. Globular clusters, on the other hand, formed in a single burst early in the galaxy's history, and no new globular clusters are forming today, at least not in galaxies like the Milky Way. They're remnants of a different era, fossils from when the universe was young and star formation was more vigorous. As we close this exploration of stellar families and clusters, consider the loneliness of our sun. Once billions of years ago, it was surrounded by siblings, part of a cluster of thousands of stars all born from the same cloud. There would have been bright, massive stars lighting up the surrounding nebula, creating a spectacular sight that Earth, had it existed then, would have witnessed. But over time, those siblings drifted away. The cluster dispersed, scattered by gravitational interactions and galactic dynamics. Today, the sun is alone, a solitary star with a retinue of planets drifting through a relatively empty region of the galaxy. Its siblings are out there somewhere, but we don't know exactly where, and the sun will never see them again. Yet the process that created the sun and its siblings continues across the galaxy. New clusters forming, new families of stars being born, and the cycle perpetuates itself endlessly. Having witnessed how stars form in groups and gradually separate, we turn now to the specific stellar nurseries, where this drama has played out most spectacularly. The famous nebulae that have captivated astronomers for centuries, and that telescopes old and new continue to reveal in stunning detail. On April 1st, 1995, the Hubble Space Telescope released an image that would become one of the most iconic photographs in the history of astronomy. 3 towering columns of gas and dust rose against a backdrop of glowing nebulosity, their edges sculpted into intricate shapes by stellar winds and radiation. The tallest pillar stretched 4 light-years from base to tip, tall enough that if you started driving at highway speed from the bottom, you wouldn't reach the top for 40 million years. This was the Eagle Nebula's Pillars of Creation, and the image captured something profound: star formation, frozen in a single moment, new suns being born inside columns of cosmic dust, while the radiation from their older siblings slowly eroded those very columns away. The pillars became an icon, but they also revealed a truth we're still grappling with today. By the time we see these structures through our telescopes, they may already be gone, destroyed by forces we can't yet observe. Ghosts of stellar nurseries haunting the night sky. If these cosmic cathedrals, these monuments to creation and destruction, move you as deeply as they move me, please take a moment to like this video and subscribe. Sharing this journey through the most spectacular stellar nurseries makes the exploration richer for all of us. The story of the Pillars of Creation begins not in 1995, but 7,000 years earlier, when the light we see today left the Eagle Nebula and began its journey toward Earth. The Eagle Nebula itself, also cataloged as Messier 16 or M16, lies about 7,000 light-years away in the constellation Serpens. It's a vast star-forming region spanning about 70 light-years, containing enough material to create thousands of stars. But the pillars, those 3 towering columns, represent only a tiny fraction of the nebula, a small region where star formation is particularly active and where the sculpting effects of massive stars are especially dramatic. The pillars are made of the same material we've discussed throughout this journey: molecular hydrogen, helium, and cosmic dust. But their shape, those dramatic columns and finger-like protrusions, tells a story of destruction as much as creation. At the heart of the Eagle Nebula is a cluster of hot young O-type stars, each dozens of times more massive than the Sun. These stars emit intense ultraviolet radiation, and this radiation is slowly eating away at the surrounding molecular cloud through a process called photoevaporation. The radiation heats the surface of the cloud, causing the gas to expand and flow away like steam rising from boiling water. But the cloud doesn't evaporate uniformly. Denser clumps of material regions with more dust or slightly higher density resist the radiation better than their surroundings. As the less dense material evaporates away, these denser clumps are left behind as pillars, columns, and other sculptural forms. The pillars are not permanent structures. They're transient, existing for perhaps a few 100,000 years before they're completely eroded away. Computer models of their evolution suggest they're being destroyed from the outside in, with the outer layers constantly evaporating, while the inner denser regions remain. At the tips of the pillars, we can see small, dense knots of material called evaporating gaseous globules, or EGGs. These EGGs are sites of active star formation, protostars, cocooned inside dense clumps of dust, protected temporarily from the destructive radiation by their surrounding material. But even these won't last forever. Eventually, the radiation will erode through the protective dust, exposing the young stars inside. When that happens, the intense radiation will blow away any remaining gas and dust around the stars, halting further accretion, and potentially preventing the formation of large planets. In 2014, nearly 20 years after the original Hubble image, the pillars were re-observed using Hubble's newer, more sensitive cameras. The new images revealed details invisible in the original, more EGGs, more embedded protostars, and intricate structures in the gas, suggesting turbulent flows and shock waves. But they also confirmed something suspected from the original observations: the pillars are doomed. Within the next few thousand years, maybe within the next few 100 years, they'll be completely eroded away, their material dispersed into space or incorporated into the newly formed stars. And here's something even more sobering. In 2007, the Spitzer Space Telescope detected evidence that a supernova might have already destroyed the pillars. Infrared observations showed a blast wave, a shell of hot gas, expanding from a point behind the pillars from our perspective. Based on the blast wave size and expansion rate, astronomers estimated that the supernova occurred about 6,000 years ago. If that's correct, and if the blast wave hit the pillars, they were destroyed around 1,000 years ago. But we won't see that destruction for another 6,000 years, because the light showing the pillars' demise hasn't reached us yet. The pillars of creation might be the pillars of destruction already gone, with us none the wiser for the next few millennia. This is one of the strangest aspects of observing distant objects. We see the past, not the present. Every astronomical observation is a look backward in time, and for objects thousands of light years away, we're seeing ancient history. The pillars we admire might be cosmic fossil structures that no longer exist, preserved only in the light that left them millennia ago. But let's shift our perspective to another spectacular stellar nursery, one even more active and closer to home, the Orion Nebula. We've mentioned Orion several times already, but now let's truly appreciate its significance. At just 1,344 light-years away, the Orion Nebula is the nearest massive star-forming region to Earth. It's visible to the naked eye as the fuzzy middle star in Orion's sword hanging below his belt. With even a small telescope, the nebula reveals its structure, a roughly circular cloud of glowing gas about 24 light-years across, with 4 bright stars at its center forming the trapezium. The Orion Nebula has been known since ancient times. Mayan astronomers recognized it as a cosmic fire or hearth, and it appears in ancient Chinese star catalogs. But it wasn't until Galileo turned his telescope toward Orion in 1610 that individual stars within the nebula were resolved. In 1656, Christian Huygens made the first detailed drawings of the nebula's structure, and in the 19th century, long-exposure photography revealed the nebula's true extent and complexity. Modern observations of Orion have transformed our understanding of star formation. The Hubble Space Telescope has observed the nebula, extensively cataloging over 3,000 stars and 700 protoplanetary disks of gas and dust around young stars where planets are forming. These disks, called proplyds, short for protoplanetary disks, are visible in Hubble images as small teardrop-shaped structures. Some are being illuminated by the trapezium star's intense radiation, glowing as they're slowly photoevaporated. Others are in shadow, visible only as dark silhouettes against the bright nebula background. One of the most intensively studied proplyds is cataloged as 114-426A disk, about twice the diameter of our solar system's Kuiper belt. High-resolution Hubble images show a bright star at the center, surrounded by a dark disk seen nearly edge-on, with a bright bow-shaped shock wave on the side facing the trapezium stars. This shock wave is where the stellar wind from the young star collides with the photoevaporating gas flowing away from the disk's surface. The disk is losing mass at a rate of about 1 Earth mass every million years, relatively slow, but still significant over the disk's lifetime. Planets may be forming inside this disk right now, condensing from the dust and gas, but they're forming under hostile conditions, bombarded by radiation and slowly losing material to photoevaporation. The 4 trapezium stars dominating Orion's core are monsters by stellar standards. The brightest Theta 1, Orionis C, is about 40 times the mass of the Sun and over 200,000 times more luminous. It's an O-type star, one of the hottest and most massive stars, known with a surface temperature of about 45,000 Kelvin. This single star produces most of the ultraviolet radiation that ionizes the entire nebula, creating the glowing gas we see. But it's also slowly destroying the nebula, eroding away the very cloud that created it. The trapezium stars are probably less than 1 million years old infants by stellar standards, yet they're already powerful enough to reshape their environment on scales of light years. Have you ever wondered what it would be like to observe a stellar nursery from inside, rather than from thousands of light years away? If you could somehow place Earth in the Orion Nebula, orbiting a star within the Trapezium cluster, the sky would be unrecognizable. The nebula would fill much of the sky as a vast glowing wall of red and green light, bright enough to cast shadows at night. The trapezium stars would blaze with incredible intensity. Theta 1 Orionis C alone being bright enough to illuminate the landscape in broad daylight, despite being light weeks away. And everywhere you looked, you'd see protostars, disks, jets, and shock waves, the machinery of star formation, visible in stunning detail. Now, let's journey to the southern hemisphere's most spectacular stellar nursery, the Carina Nebula, one of the largest and most active star-forming regions in the Milky Way. Located about 8,500 light-years away in the constellations Carina, this nebula spans over 300 light-years, making it over 10 times larger than Orion. It contains several open clusters, dozens of massive O-type stars, and at least 60,000 stars in total. But Carina's true claim to fame is Eta Carinae, one of the most massive and luminous stars known. Eta Carinae is a stellar behemoth estimated to contain between 100 and 150 solar masses, right at the upper limit of what a star can be. It's so luminous, about 5 million times more luminous than the Sun, that radiation pressure from its intense light nearly tears the star apart. In the 1840s, Eta Carinae underwent a massive eruption called the Great Eruption, becoming briefly the second brightest star in the night sky, despite being thousands of light years away. During this eruption, the star ejected about 10 to 20 solar masses of material, creating a bipolar nebula called the Homunculus Nebula that still surrounds the star today. Eta Carinae is unstable, variable, and unpredictable. It could explode as a supernova tomorrow, or it could continue shining for another 10,000 years before collapsing. When it does explode, it will be one of the brightest supernovae ever observed, potentially visible in broad daylight and casting shadows at night. And that explosion will trigger a new wave of star formation in the Carina Nebula, compressing nearby gas clouds and starting the cycle again. The Carina Nebula has been extensively photographed by both ground-based telescopes and the Hubble Space Telescope. In 2007, Hubble released a mosaic image of the nebula, comprising over 48 individual frames, revealing unprecedented detail across a 50 light-year swath of the nebula. The image shows towering pillars similar to those in the Eagle Nebula, dense globules where stars are forming, and vast expanses of ionized gas glowing in shades of red, orange, and blue. Scattered throughout are massive young stars, each one a powerhouse of energy, each one reshaping its environment. One particularly striking feature in the Carina Nebula is a structure called the Mystic Mountain, a 3 light-year tall pillar of gas and dust, photographed by Hubble in 2010 to commemorate the telescope's 20th anniversary. Like the pillars of creation, the Mystic Mountain is being sculpted by intense radiation from nearby massive stars. At its peak is a jet from a young star shooting outward and creating a shockwave as it plows into the surrounding gas. The image is hauntingly beautiful, a cosmic landscape that looks almost painted, yet it's entirely real, entirely natural. The product of physics and chemistry operating on scales beyond human intuition. Let's venture even farther beyond our galaxy to the Tarantula Nebula in the Large Magellanic Cloud, a small satellite galaxy orbiting the Milky Way about 160,000 light-years away. The Tarantula Nebula, also called 30 Doradus, is the largest and most active stellar nursery in the local group of galaxies. It's so luminous that if it were located at the same distance as the Orion Nebula, just 1,300 light-years away, it would cast shadows on Earth and be bright enough to read by at night. The nebula spans about 600 light-years and contains hundreds of thousands of young stars, including some of the most massive stars ever discovered. At the heart of the Tarantula Nebula is a superstar cluster called R136, containing over 200 very massive stars packed into a region just a few light years across. Several stars in R136 exceed 150 solar masses, pushing the theoretical limit of stellar mass. One star, R136A1, is estimated to have been born with about 315 solar masses, though it's already lost substantial mass through intense stellar winds. These ultramassive stars are extraordinarily rare. There are probably only a few dozen such stars in the entire observable universe, and several of them are concentrated in this single cluster. The Tarantula Nebula also holds a significant place in astronomical history. In February 1987, a massive star in the Tarantula Nebula's outskirts exploded as supernova 1987. A, the nearest supernova observed in modern times. For months, ASN 1987. A was visible to the naked eye from the southern hemisphere, and it's been studied intensively ever since, providing crucial insights into supernova physics and stellar evolution. The explosion is still expanding, and the shockwave is now interacting with a ring of material ejected by the star thousands of years before it exploded, creating a spectacular light show visible in Hubble images. As we compare these famous stellar nurseries, a pattern emerges. They're places of simultaneous creation and destruction, where new stars are being born even as older stars destroy the clouds that created them. They're ephemeral on cosmic timescales, existing for just a few million years before dispersing. And they're crucial to galactic evolution, recycling gas and dust, enriching the interstellar medium with heavy elements and perpetuating the cycle of stellar birth and death. But our view of stellar nurseries has been revolutionized in just the past few years by a new telescope that sees farther and deeper than any before it. In December 2022, the James Webb Space Telescope released its first images of star-forming regions, and what we saw was astonishing. Webb observed the pillars of creation, with its infrared cameras seeing through the obscuring dust to reveal hundreds of protostars invisible to Hubble, glowing like rubies embedded in the pillar's structure. Webb observed the Carina Nebula, revealing the intricate structure of gas and dust at unprecedented resolution, showing individual protostars, jets, and shock waves with clarity that would have been impossible just a few years ago. The difference between Hubble's visible light images and Webb's infrared images is like the difference between looking at a fog bank and seeing through it. Visible light is blocked by dust, so Hubble sees only the surfaces of dense clouds. Infrared light penetrates the dust, allowing Webb to see inside the clouds to where star formation is actually occurring. The protostars that were merely implied in Hubble images are directly visible in Webb images, glowing in infrared as they accrete material and heat up. These observations aren't just aesthetically beautiful, they're scientifically transformative. By seeing inside stellar nurseries, we can count how many stars are forming, measure their masses, observe their disks, and track their evolution in ways that were impossible before. Webb is allowing us to test theoretical models of star formation against direct observations, refining our understanding of how stars and planetary systems come into being. And we're only at the beginning. Webb's mission is planned to last at least 10 years, possibly 20 or more. And every year will bring new discoveries, new insights, and new images that reshape our understanding of how the universe creates its stars. Having witnessed these particular spectacular stellar nurseries, and how our ability to observe them has evolved over time, we now step back to consider the broader significance of what we've learned, examining how the birth of stars and nurseries like these shapes not just individual solar systems, but entire galaxies over cosmic history. Every year, in our Milky Way galaxy, alone approximately 2 solar masses worth of hydrogen and helium collapse into stellar nurseries and begin their transformation into stars. 2 times the mass of our entire sun every single year, converted from diffuse gas into concentrated stellar cores. That might not sound like much when you consider that our galaxy contains over 200 billion stars already, but compound that rate over 1 billion years, and you've created 2 billion new suns. Over the galaxy's entire 13 billion year history, the cumulative effect is staggering. But here's what makes this truly profound. Those stars don't just sit there shining. They live, they evolve, and when they die, they give back. Massive stars explode as supernovae, scattering heavy elements across light years. Smaller stars shed their outer layers as planetary nebulae, enriching the interstellar medium with carbon and nitrogen. This material becomes the seed for the next generation of stellar nurseries, creating a cycle of birth, death, and rebirth that has fundamentally shaped our galaxy's structure, chemistry, and evolution over cosmic time. If the idea that stellar birth shapes entire galaxies, that individual stars rippling outward to affect billions of others resonates with you, please like this video and subscribe to the channel. Understanding these cosmic connections helps us see ourselves as part of a much larger story. Let's begin by quantifying exactly how active star formation is in the Milky Way. That figure of 2 solar masses per year. Our galaxy's star formation rate comes from decades of careful observation, combining multiple methods. Astronomers count young massive stars whose lifetimes are short enough that they must have formed recently. They measure infrared emission from warm dust heated by newly formed stars. They detect radio emission from ionized hydrogen in stellar nurseries. All these methods converge on approximately the same number 2 solar masses per year, give or take about 50%, depending on the method and the uncertainties involved. This rate is actually relatively modest compared to some galaxies. The Milky Way is what astronomers call a normal star-forming galaxy, creating new stars at a steady, sustainable pace. But to understand why this matters, we need to understand what happens to the interstellar medium, the gas and dust between the stars as star formation proceeds. Before the first stars formed, the universe contained only hydrogen, helium, and trace amounts of lithium, all created in the Big Bang. There was no carbon, no oxygen, no silicon, no iron, none of the elements essential for planets and life. These heavier elements, which astronomers collectively call metals, regardless of their actual chemical properties, had to be created inside stars through nuclear fusion, and then returned to the interstellar medium through stellar winds, planetary nebulae, and supernova explosions. This process is called chemical enrichment, and it's one of the most important consequences of star formation. Every generation of stars takes in relatively metal-poor gas and returns metal-enriched gas to the interstellar medium. The enrichment is gradual but cumulative. The first stars, called population 3 stars, formed from completely pristine gas and had 0 metallicity. When they exploded as supernovae, they enriched their surroundings with the first heavy elements. The second generation in population 2, stars formed from slightly enriched gas and had low but non-zero metallicity. When they died, they further enriched the medium. And this process has continued for over 13 billion years, each generation slightly more metal-rich than the last. Our sun is a population 1 star, a relatively recent star formed about 4.6 billion years ago, from gas that had already been enriched by many previous generations of stars. The sun's metallicity is about 1.34% by mass, meaning that about 1.34% of its mass consists of elements heavier than helium. That might sound small, but it's enormous compared to the earliest stars. Population 2 stars typically have metallicities 100 or 1,000 times lower than the sun's. Population 3 stars, which we've never directly observed, would have had metallicities of essentially 0. This chemical enrichment has profound consequences for planet formation. Planets, especially rocky planets like Earth, are made almost entirely of heavy elements: iron, silicon, oxygen, magnesium, and others. In the early universe before stars had enriched the interstellar medium, there simply wasn't enough of these elements to form planets. The first stars probably didn't have planetary systems, or if they did, those planets were radically different from anything we see today, perhaps made of exotic materials we can barely imagine. As metallicity increased over cosmic history, planet formation became more efficient. More dust grains condensed in protoplanetary disks. Those grains collided and stuck together more readily. Larger planets could form more quickly. By the time our solar system formed 4.6 billion years ago, metallicity was high enough that Earth-like rocky planets could form efficiently. We owe our existence to billions of years of chemical enrichment, to countless generations of stars that lived, died, and gave back their processed material to the cosmos. But chemical enrichment is just one way star formation shapes galaxies. Another crucial mechanism is feedback, the process by which stars affect their environment and regulate future star formation. We've already discussed some forms of feedback: stellar winds clearing away gas, supernovae triggering new star formation, photoevaporation destroying molecular clouds. But let's examine these processes more carefully and understand their galactic scale implications. When a massive star forms, it doesn't just shine passively. It actively reshapes its surroundings. The intense ultraviolet radiation ionizes nearby gas, heating it to tens of thousands of Kelvin. This hot ionized gas creates pressure, pushing against the surrounding neutral gas and carving out bubbles. These bubbles can grow to hundreds of light years in diameter, clearing vast regions of space. Multiple massive stars in a cluster create overlapping bubbles that merge into superbubbles, enormous cavities in the interstellar medium. The Orion Eridanus superbubble, associated with the Orion Molecular Cloud Complex, is one of the nearest superbubbles to Earth. It spans about 1,200 light years and extends from the constellation Orion into Eridanus. This structure was created over the past 10 million years by multiple generations of massive stars, forming in the Orion region their stellar winds and supernova explosions, excavating a giant cavity in the interstellar medium. The shell of this superbubble is visible in X-ray and radio observations glowing from the hot, shocked gas. Superbubbles have a dual effect on star formation. They destroy molecular clouds within them, shutting down star formation in the regions they clear. But they also compress gas at their edges, triggering new star formation in shells around the bubble. This creates a pattern of sequential star formation waves spreading outward from the initial stellar nursery, each wave triggering the next. When massive stars explode as supernovae, their impact is even more dramatic. A single supernova releases about 10 to the 51st ergs of energy, equivalent to all the energy our sun will emit over its entire 10 billion year lifetime, released in a few seconds. This energy goes into accelerating the stellar debris outward at speeds up to 10% the speed of light, and into driving a shockwave through the surrounding interstellar medium. That shockwave can trigger star formation hundreds of light years away, compressing molecular clouds and initiating gravitational collapse. But supernovae don't just trigger star formation. They also inject enormous amounts of energy into the interstellar medium heating gas and potentially driving it out of the galaxy entirely in a process called galactic winds. In galaxies with very high star formation rates, the collective effect of many supernovae can create outflows powerful enough to eject gas from the galaxy's gravitational, while removing the raw material for future star formation and potentially quenching star formation altogether. This brings us to one of the most important concepts in understanding galactic evolution. The star formation rate must be self-regulating. If star formation were too efficient, if every bit of gas immediately collapsed into stars, galaxies would convert all their gas into stars very quickly, then run out of material and stop forming new stars. Conversely, if feedback were too strong, If supernovae and stellar winds immediately ejected all the gas from galaxies, star formation would shut down prematurely. The observed fact that galaxies like the Milky Way have been forming stars at relatively steady rates for billions of years suggests a delicate balance, a feedback loop where star formation regulates itself. This self-regulation occurs through multiple mechanisms. Star formation creates massive stars. Massive stars produce feedback that heats and ejects gas. This reduces the amount of cold, dense gas available for star formation, which lowers the star formation rate. With a lower star formation rate, feedback decreases, allowing gas to cool and accumulate again, which increases the star formation rate. The system oscillates around an equilibrium, maintaining a roughly constant average star formation rate over time. Computer simulations of galaxy formation and evolution now routinely include these feedback processes, and getting the feedback right is crucial for matching observations. Early simulations without strong feedback produced galaxies that were far too massive and had converted too much of their gas into stars. Modern simulations with realistic feedback reproduce observed galaxy properties much better, showing that feedback is not just a minor detail, but a fundamental part of how galaxies work. Now, let's consider how star formation rates have evolved over cosmic history. This is one of the most important questions in observational cosmology. How has the universe's star formation rate changed over time? By observing galaxies at different distances, which means looking at them at different epochs in cosmic history. Because light takes time to travel, astronomers have reconstructed the universe's star formation history. The results are striking. Star formation in the universe was not constant over time. It peaked about 10 to 11 billion years ago, when the universe was 2 to 3 billion years old, at a rate about 10 to 20 times higher than today. This epoch, sometimes called cosmic noon, was the most active period of star formation in the universe's history. Galaxies at cosmic noon were forming stars at prodigious rates, often hundreds or even thousands of solar masses per year in the most extreme cases. Since cosmic noon, the universal star formation rate has been declining steadily. Today, the universe forms stars at only about 5 to 10% of its peak rate. This decline is partly due to galaxies consuming their available gas, but it's also due to feedback processes becoming more efficient at suppressing star formation as galaxies evolve. The universe is gradually settling down, becoming less active, less violent, more quiescent. This decline will continue into the future. Billions of years from now, most galaxies will have exhausted their cold gas reservoirs and will no longer form stars at significant rates. The universe will enter an era dominated by long-lived low-mass stars, with only occasional star formation events when galaxies collide and merge temporarily, rekindling star formation through the compression of their remaining gas. But there are exceptions to this cosmic slowdown: galaxies that are forming stars at extraordinarily high rates even today. These are called starburst galaxies, and they represent some of the most extreme environments in the universe. Starburst galaxies form stars at rates hundreds or even thousands of times higher than normal galaxies like the Milky Way. Instead of 2 solar masses per year, a starburst galaxy might form 1,000 solar masses per year or more. The nearest major starburst galaxy is M82, also called the Cigar Galaxy, about 12 million light-years away in the constellation Ursa Major. M82 is forming stars at about 10 times the rate of the Milky Way, despite being smaller. And this intense star formation is driven by a gravitational interaction with its larger neighbor, M81. The gravitational tidal forces from M81 have compressed gas in M82's core, triggering an intense burst of star formation that has been ongoing for about 200 million years. Observations of M82 in multiple wavelengths reveal the consequences of this starburst. In visible light, the galaxy appears to have plumes of gas and dust extending above and below its disk, ejected by the collective stellar winds and supernovae from thousands of massive stars. In X-ray light, the galaxy glows brilliantly from hot shocked gas, the remnants of supernova explosions and stellar winds. In radio, we detect synchrotron emission from relativistic electrons accelerated by the intense magnetic fields generated by the starburst. M82 is a galaxy in the throes of violent star formation, and it's tearing itself apart in the process. Starburst galaxies can't sustain their extreme star formation rates for long. At M82's current rate, it would consume all its available gas in about 1 billion years, maybe less. Most likely, the starburst will end sooner than that, as feedback from the newly formed stars heats and ejects the remaining gas, quenching further star formation. Starburst galaxies are transient phenomena flaring up for a few 100 million years, then fading back to normal or even becoming quiescent. The chemical evolution of galaxies follows a predictable pattern called the mass-metallicity relation. More massive galaxies have higher metallicities. This seems counterintuitive at first. Why should larger galaxies be more metal-rich? The answer lies in gravitational potential. More massive galaxies have deeper gravitational wells, making it harder for supernova-driven winds to eject enriched gas into intergalactic space. The enriched material stays in the galaxy, gets incorporated into subsequent generations of stars, and gradually builds up the overall metallicity. Smaller galaxies with shallower gravitational wells lose more of their enriched gas to outflows, preventing their metallicity from rising as high. Our Milky Way's metallicity has increased by about a factor of 20 over the past 13 billion years, from the low metallicities of the oldest stars in our galaxy to the solar metallicity of stars forming today. This enrichment history is written in the chemical compositions of stars of different ages. By measuring stellar metallicities and ages, we can reconstruct the galaxy's chemical evolution and understand how star formation and feedback have shaped the Milky Way over cosmic time. There's a profound philosophical dimension to this story of chemical enrichment. Every atom in your body heavier than hydrogen was created inside a star. The oxygen you breathe, the carbon in your DNA, the calcium in your bones, the iron in your blood, all of these were forged by nuclear fusion in stellar cores, then scattered into space by stellar winds or supernova explosions. You are made of stardust, not as a poetic metaphor, but as a literal fact. The atoms comprising your body have cycled through multiple generations of stars, each time being processed, enriched, and returned to the interstellar medium, until finally they found their way into the molecular cloud that collapsed to form our solar system 4.6 billion years ago. This means stellar nurseries are not just creating stars, they're creating the building blocks of planets, atmospheres, oceans, and life itself. Every stellar nursery is a forge of creation, transforming the simplest elements into the complex materials that make worlds and perhaps make consciousness possible. The Orion Nebula, the Eagle Nebula, the Carina Nebula. All of these are doing more than birthing stars. They're creating the raw materials for future Earths, future civilizations, future beings who will look up at their own skies and wonder about their place in the cosmos. As we absorb these galactic-scale implications, understanding how individual stellar nurseries ripple outward to shape entire galaxies over billions of years, we're ready for our final reflection, a chance to step back and contemplate the full cycle of cosmic birth we've explored, from the first tremors in a molecular cloud to the eventual scattering of stellar families across space, and to consider what this means for us, beings made of atoms forged in stellar nurseries living on a planet born from stellar debris, looking up at a sky filled with nurseries creating the next generation of stars and worlds. We've traveled together through the complete life cycle of stellar birth, from the first tremors in a cold molecular cloud to the moment of nuclear ignition when a star finally awakens. We've seen how gravity patiently gathers matter over millions of years, how dust and gas conspire to create the conditions for fusion, how stellar siblings are born together, then scattered across the galaxy by time and chance. But now, as we approach the end of our journey, I want us to step back and contemplate what all of this means, not just for stars, but for us, for Earth, for every atom in your body, and for the future of the universe itself. There's a paradox at the heart of stellar nurseries that I find endlessly beautiful. Stars are born from death. Every stellar nursery we've discussed, from the Orion Nebula to the Pillars of Creation, from the Carina Nebula to the Taurus molecular cloud, contains material that was once inside other stars. The heavy elements, the cosmic dust, even the trigger that initiates collapse. These often come from stars that exploded as supernovae or shed their outer layers as planetary nebulae. Death feeds birth. Destruction enables creation. The universe recycles itself endlessly, and nothing is ever truly lost. This cycle has been operating for over 13 billion years, since the first stars formed just a few 100 million years after the Big Bang. Those first stars, the population 3 stars, were radically different from anything we see today. They formed from completely pristine gas, pure hydrogen and helium, with no heavy elements at all. They were probably extremely massive, perhaps hundreds of times the mass of our sun. And they lived fast, burning through their fuel in just a few million years before exploding as supernovae. But those explosions were crucial. They scattered the first heavy elements into space carbon and oxygen and silicon and iron, created through fusion in the stellar cores and in the supernova explosions themselves. Those heavy elements mixed into the surrounding gas, and when the next generation of stars formed, they formed from slightly enriched material. Generation after generation, the interstellar medium has been enriched, each cycle adding more heavy elements, building up the cosmic abundance of metals from essentially zero to the roughly 2% we see in stellar nurseries today. This process of chemical enrichment is why you exist. Your body contains about 60 chemical elements, and all of them except hydrogen were created inside stars. The oxygen you're breathing right now was created in the core of a massive star that exploded as a supernova probably about 5 to 7 billion years ago. The carbon that forms the backbone of every organic molecule in your body, your DNA, your proteins, your cell membranes, was created through a process called the triple alpha process in the core of a red giant star. The calcium in your bones, the iron in your blood, the phosphorus in your ATP, all of these were created through nuclear fusion inside stars and then scattered into space when those stars died. In 2014, astronomer Carl Sagan popularized the phrase, "We are made of star stuff," and it's become something of a cliche. But I don't think people fully appreciate how literally true it is. It's not a metaphor. It's not poetic exaggeration. It's a physical fact verified by spectroscopy and nuclear physics. The atoms in your body were forged inside stellar cores at temperatures of hundreds of millions of degrees, then blown into space by stellar winds or supernova explosions, then spent millions or billions of years drifting through the interstellar medium, then eventually found their way into the molecular cloud that collapsed to form our solar system 4.6 billion years ago. Those atoms were incorporated into the dust and gas that built the planets, and eventually 4 billion years ago, some of those atoms were incorporated into the first living organisms on Earth. Those atoms have been cycling through the biosphere ever since, through countless organisms, through ecosystems, through evolutionary history, until finally, by chance, they ended up in you. Think about that for a moment. The atoms in your left hand might have come from one ancient star. The atoms in your right hand might have come from a different star that exploded at a different time in a different part of the galaxy. You are an assemblage of stellar debris pieces of dozens or hundreds of different stars that lived and died billions of years ago, now temporarily organized into a conscious being that can contemplate its own origin. Is that not astonishing? But stellar nurseries aren't just our past, they're also our future, or at least the future of the cosmos. Right now, as I speak, these words stellar nurseries across the Milky Way are creating new stars. The Orion Nebula alone is forming dozens or hundreds of stars at this very moment. Some of those stars will be similar to our Sun. They'll have protoplanetary disks where planets will form. Some of those planets will be rocky worlds orbiting in the habitable zone, where liquid water can exist. And on some fraction of those worlds, perhaps life will emerge, perhaps even intelligent life. It's possible, perhaps even likely, that among the stars forming today in the Orion Nebula or the Carina Nebula or countless other stellar nurseries throughout the galaxy, there are solar systems where billions of years from now, beings will look up at their night sky and wonder about their origins just as we do. The universe is doing more than creating stars. It's creating the conditions for consciousness, for intelligence, for beings who can contemplate the cosmos and understand their place within it. But here's something sobering to consider. Star formation is not eternal. It can't continue forever because it requires raw materials, cold gas, and dust. And those materials are gradually being consumed. Every time a star forms, it removes some of that raw material from the interstellar medium. Some of it gets locked up in stars permanently. Some gets returned to space when the star dies, but not all of it. And the efficiency of recycling is not 100%. Over billions of years, the galaxy's reservoir of star-forming gas is slowly being depleted. We know from observations of distant galaxies that the universe's star formation rate has been declining since cosmic noon, about 10 to 11 billion years ago. Back then, galaxies were forming stars at rates 10 to 20 times higher than today. The universe was younger, gas was more abundant, and galaxy collisions were more frequent, all factors that promoted vigorous star formation. Since then, star formation has been steadily declining. Today, the Milky Way forms about 2 solar masses worth of new stars per year. Billions of years from now, that rate will be even lower. Models of galactic evolution suggest that in about 1 to 2 billion years, the Milky Way's star formation will drop to less than 10% of its current rate. In 5 to 10 billion years, star formation in our galaxy will be essentially finished, except for occasional bursts triggered by galaxy mergers. The stellar nurseries will go dark. The Orion Nebula will have dispersed or been consumed. The molecular clouds will be gone, converted entirely into stars, or ejected from the galaxy by supernovae and stellar winds. And this isn't just happening in the Milky Way. It's happening throughout the universe. As galaxies age and consume, their gas star formation gradually ceases. The universe is entering an era of decline, slowly transitioning from an active star-forming cosmos to a quiescent cosmos dominated by long-lived low-mass stars and the remnants of dead stars. This long decline will continue for trillions of years. The low-mass red dwarf stars forming today will still be shining 50 trillion, 100 trillion years from now, long after stars like our Sun have exhausted their fuel and died. But eventually, even the red dwarfs will burn out. The last star in the universe will form at some point in the future, perhaps tens or hundreds of billions of years from now. After that, no new stars will be born. The stellar nurseries will be silent forever. But we're not there yet. Not even close. The universe is only 13.8 billion years old, still quite young in the grand scheme of cosmic time. Star formation continues vigorously in many galaxies. The stellar nurseries are still active, still creating, still doing their ancient work of transforming gas into stars, stars into planets, and perhaps planets into life. And we have the extraordinary privilege of living during the era when we can observe this process. We have telescopes that can peer into stellar nurseries and watch stars being born. The James Webb Space Telescope, launched in December 2021, is revolutionizing our understanding of star formation by observing stellar nurseries in unprecedented detail. Webb's infrared cameras can see through the dust that blocks optical light, revealing protostars in their cocoons. protoplanetary disks in the act of forming planets and the intricate structures of molecular clouds at scales never before possible. In September 2022, Webb released images of the pillars of creation observed in infrared light, and what we saw was stunning. Hubble's famous visible light images show the pillars as dark silhouettes against glowing nebulosity, beautiful but opaque. Webb's infrared images show through the dust, revealing hundreds of protostars glowing like rubies embedded in the pillar's structure. Stars that were completely invisible to Hubble suddenly appeared in Webb's view. Each one a newborn sun surrounded by its accretion disk, each one potentially creating its own planetary system. Webb has also observed the Carina Nebula, revealing an astonishing landscape called the Cosmic Cliffs, a region where intense radiation from massive stars is eroding away a molecular cloud, revealing layer after layer of structure and embedded protostars. The images look almost painted, almost unreal in their beauty, yet they're entirely real, entirely natural, the product of physics operating at scales beyond human intuition. These observations aren't just aesthetically beautiful, they're scientifically transformative. By seeing inside stellar nurseries, by counting protostars at different stages of development, by measuring their masses and temperatures and accretion rates, we're testing our theoretical models of star formation against reality. And what we're finding is both confirming and surprising. The basic picture we've developed over decades of research is largely correct, but the details are far richer and more complex than we imagined. For instance, we're discovering that the efficiency of star formation is surprisingly low. When a molecular cloud collapses, only about 1 to 5% of its mass actually ends up in stars. The rest is dispersed by stellar winds, photoevaporation, and supernovae before it can collapse. This inefficiency is actually crucial for galactic evolution. If star formation were highly efficient, galaxies would convert all their gas into stars very quickly, and then become quiescent within a billion years. The observed inefficiency prolongs star formation, allowing it to continue over the galaxy's lifetime. We're also discovering that stellar nurseries are more dynamic and violent than we thought. The radiation and winds from massive stars don't just gently sculpt the surrounding gas. They can completely disrupt star-forming regions, halting star formation in some areas while triggering it in others. The feedback from stars regulates the star formation process, creating a complex interplay between creation and destruction that determines how many stars ultimately form. And we're finding that planet formation begins almost immediately. The ALMA observations of H.L. Tauri, which we discussed earlier, show clear evidence of planet formation in a system less than 1 million years old, far younger than anyone expected. Planets don't wait for the star to finish forming. They begin assembling in the protoplanetary disk, even while the protostar is still accreting material. This means that planet formation is a rapid, efficient process, and it suggests that planetary systems like ours are probably common throughout the galaxy. This brings us back to a question that underlies everything we've discussed. Are we alone? In a galaxy with hundreds of billions of stars, where stellar nurseries are creating thousands of new stars every year, where planet formation appears to be a natural and common outcome of star formation, where the building blocks of life are being synthesized in molecular clouds even before planets form, are we the only conscious beings, or is the universe filled with life, with intelligence, with civilizations, looking up at their own skies and asking the same questions we're asking? We don't know the answer yet. Despite decades of searching, we haven't detected any definitive evidence of extraterrestrial intelligence. But the search continues, and our tools are getting better. The discovery of thousands of exoplanets over the past 2 decades has shown us that planets are ubiquitous. Nearly every star has planets. Some of those planets are rocky worlds orbiting in the habitable zone. The ingredients for life are common. The environments where life could emerge are common. Whether life actually emerges in those environments and whether it evolves to intelligence remains unknown, but the possibilities are tantalizing. If life and intelligence are common in the universe, then stellar nurseries are creating not just stars and planets, but the potential for consciousness for beings who can contemplate the cosmos and understand their place within it. Every stellar nursery might be creating future civilizations, future scientists and philosophers and artists who will look up at their skies and feel the same sense of wonder we feel. And if that's true, then the work being done in stellar nurseries right now, the patient gathering of gas, the slow collapse, the ignition of fusion, the formation of planets, all of this is profoundly important. It's the universe becoming aware of itself. Atoms arranged in patterns complex enough to ask questions about their own origins. As I close this exploration of stellar nurseries, I want to leave you with a thought that brings the entire story full circle. Every stellar nursery we've discussed, from the nearest ones, just a few hundred light years away, to the most distant ones, billions of light years away, is simultaneously past, present, and future. When we observe a stellar nursery, we're seeing ancient history light that left that region thousands or millions of years ago. But we're also seeing the present unfolding stars being born right now, even if we won't see the results of that birth for thousands of years. And we're seeing the future because the stars forming today will be the suns that warm future worlds billions of years hence. The universe is not a static place. It's a story still being written, a story of matter organizing itself into ever more complex forms, from hydrogen atoms to molecular clouds to stars to planets to life to consciousness. And we are part of that story, not observers from outside, but participants within it, made of the same atoms as the stars, following the same physical laws, emerging from the same cosmic processes that have been operating since the beginning of time. The stellar nurseries are still at work, still gathering gas, still collapsing, still igniting fusion. The cycle continues. And it will continue for billions of years to come, creating new suns, new worlds, new possibilities. The universe is still young, still creative, still capable of astonishing beauty and complexity. And we are privileged to be here now, in this moment of cosmic history, able to look up at the stars and really understand where they came from and where we came from, and how we're all connected in the grand tapestry of creation. So, the next time you look up at the night sky, remember that you're not just seeing distant points of light, you're seeing family. Those stars were born in stellar nurseries from the same cosmic materials that made you. Some of those stars have planets. Some of those planets might harbor life. And some of that life might be looking back at you across the light years, wondering if they're alone. You're not looking at the universe from outside. You're the universe looking at itself, a way for the cosmos to know itself, to understand itself, to appreciate its own beauty and complexity. The atoms in your body were forged in stellar cores and scattered by dying stars. You are quite literally made of stardust, a conscious assemblage of stellar debris contemplating its own origin. And that, I think, is the most profound realization to emerge from our understanding of stellar nurseries. We are not separate from the cosmos. We are the cosmos, a part of it, an expression of it, perhaps the universe's way of understanding itself. Thank you for joining me on this journey through the stellar nurseries, through the places where stars are quietly born. I hope you found wonder in the science piece and the vastness, and perhaps a new appreciation for the deep connections between the stars and ourselves. The universe continues its work of creation even as we speak, and there are countless more stories waiting to be told about the cosmos and our place within it. Until we meet again under the stars, keep looking up, keep wondering, and keep asking questions. The universe loves to be understood.